the introduction. He's the network connection. There is some problem. Next, Anand. Yeah, we as Epicons Friends of Concrete started in 1998. Our inspiration is Remedius. Next, we have been doing workshops with various eminent personalities in the field. You can see all the stalwarts in the field here. And you can see Dr. Yogendra Singh and Mr. MG, Professor MG Gadgil also in that. So these two all will be giving today's lecture. Next. This is our Epicons team, Epicons management team. Next, these are our volunteers who are the main thing. And I'll just give you introduction of Dr. Yogendra Singh. He is the currently Railway Bridge Chair Professor and Professor of Earthquake Engineering at Indian Institute of Technology, Roorkee. He Civil from IIT Roorkee 1989, MTech PhD in Structural Engineering from IIT Delhi. Various research interests includes performance-based design, vulnerability and risk evaluation, non-linear modeling and analysis, and retrofitting of structures. About 25 years of research and teaching experience, and guided 13 PhDs, published 65 research articles in various journals, member of several expert teams for post-earthquake damage surveys, convener of the BIS expert group on performance-based design, and collaborated with various universities and initiatives in the continuing education field. I'll request Dr. Yogendra Singh to start his lecture.
Thank you very much, Parulekar Saab, for giving this opportunity. And I'm thankful to all the participants for joining this afternoon in such a large number. So I will start the talk. So I hope all can see my screen now. So this is the topic for today, seismic design of code exceeding buildings. So the key word here is code exceeding. And you may ask me that what is meant by code exceeding? Why the buildings exceed code? And which buildings we will say that those are code exceeding? And this term code exceeding is in context of earthquake only, or code exceeding buildings are in the context of gravity and other effects as well. So code exceeding in general, anything which is not covered by code, because codes have certain limitations, and anything which is beyond the code, practice is always beyond the code. So many new things come in the market, many new innovations people invent, and codes always follow the practice and theory. So buildings which we are constructing in field exceed the code, and those may exceed in terms of material. So we may use a grade of concrete which is higher than what is covered by the code. There are height of the buildings which may be taller than what is covered by the code. But in case of earthquake, it has a slightly different meaning. So when we talk about code exceeding buildings in context of earthquake resistant design, it means that invariably the building has some irregularity, so some abnormality. So that type of buildings we are causing primarily the code exceeding buildings. And the reason for exceeding the code lies in the nature of earthquake force itself. So this figure, perhaps most of you are familiar. This is record of an earthquake. And what we see here is that earthquake changes its direction continuously with time. And the change is very quick. Within a fraction of a second, the acceleration is changing its direction. And the force which is acting on the structure, which is mass into acceleration, that force also changes its direction. And this is unique property of earthquake force. No other action which we usually consider in design of our structures is having this property. It does not have such reversal. Wind has a fluctuating nature, but that fluctuation is occurring about a mean wind velocity. So the direction reversal is not there in case of wind. And in case of earthquake, we take advantage of this reversal. Because the problem with, another problem with earthquake is that it is a very large force. So compared to other forces, the magnitude of the force caused by earthquake is very, very large. And as a result, if we want to design our structure to remain elastic under that force, then the material required will be huge. So what we do, we allow our structure to yield. We do not design our structure for the full earthquake force, which will be applied on an elastic structure. Rather, we design for a lower capacity. And when the structure is designed for lower capacity, and you may be knowing that we are usually designing for about 10 to 20% of the earthquake force only. And when the earthquake force is larger than the capacity of the structure yields. And the direction of the force reverses very quickly. So the structure yields, but it does not collapse. Before it reaches the collapse state, the reversal of the earthquake force occurs. And the structure undergoes a cyclic response, due to which there is hysteresis and there is dissipation of energy. And the earthquake energy gets dissipated by the hysteresis of the structure. And as a result, the structure is able to dissipate or able to resist forces due to earthquake much larger than its capacity, by the virtue of this inelastic energy dissipation due to the cyclic nature of earthquake. In our conventional analysis, we take this cyclic energy dissipation, inelastic energy dissipation, into account indirectly using the so-called response reduction factor. This response reduction factor takes into account the inelastic energy dissipation, and it allows us to use linear analysis for the structure which is actually going into inelastic behavior, into nonlinear behavior. So as we do not design our structure to remain elastic during earthquake, all the structures designed even with the latest codes will undergo inelastic deformation. So it will go into inelastic response, and there will be inelastic energy dissipation. But there is a very important observation which has been done by many researchers based on a number of analyses. And this observation is that the maximum displacement of an elastic and inelastic structure is same. This we call a principle of equal displacement. So this equal displacement principle can be understood like this. This red line is showing the behavior of an elastic structure. Elastic structure means a linear elastic structure, that it will be the load versus displacement. Here the base shear versus roof displacement we can take. That is given by a linear response, a linear curve. And the maximum force which will occur on the elastic structure is equal to VE, and the corresponding displacement is delta M or delta E, the elastic displacement. But in reality, my structure will never have this much capacity. The structure will have much lower capacity, let us say equal to Vy, and the ratio of these two, Vy and Ve, this is representing our response reduction factor, which we use in our linear analysis. So we never design for Ve, we design for this Vy. And our structure cannot take load beyond Vy because we have not designed it for that force. And after that, its behavior will become horizontal. It will be given by this horizontal line. That means the displacement will increase, but the force is not going to increase. Interesting thing is that the maximum displacement of these two structures is same, delta M, the elastic structure as well as inelastic structure. And with some geometry, we can do some simplification, and the ductility ratio we define as this maximum displacement by yield displacement, delta M by delta Y, and the response reduction factor R is this VE by Vy. So we can see from the similar triangles, this ratio of V by Vy is same as the ratio of delta M by delta I, and the relationship mu equal to R we obtain. That means the response reduction factor which we can use in our structures while designing them using linear analysis is equal to the ductility ratio, the displacement ductility ratio of the structure mu. And larger the ductility the structure possesses, we can afford it to design for lower force. For example, if my structure has larger ductility ratio than this, then I can design for even smaller force. In that case, the structure will yield at much lower force, or we can design it for much lower force. If the ductility ratio is less, let us say somewhere here, then we have to design it for larger base shear, or the response reduction factor will be smaller. So the structure resists the earthquake action by combination of strength and ductility. And obtaining ductility is not easy. Whatever we study in our steel or concrete design, that is about estimating strength. But we do not study much about estimating ductility. So to simplify the life of a designer, the code indirectly takes into account this ductility in the form of this response reduction factor R. But what we have to understand is that this R is based upon past experience, and it is specified for classes of buildings. This is not specified for individual buildings. This is specified for the class of the buildings. So if you have a look at IS 1893, there are response reduction factors given for different classes of the building. And that classification of the buildings or structures is based on two things. One is the material of construction, and another is the structural system. So it is representing the average structure in that category. If my structure is different, it is not close to the mean structure, it is abnormal structure, then of course this response reduction factor is not valid. And that's precisely the reason why our buildings have code exceeding, our code exceeding. And we have to do something to take into account that abnormality, which is because of not following the average characteristics of the code. That's why the codes specify that those buildings for which the code-based method can be used has certain features. Those features are specified in terms of do's and don'ts. So we have to follow those do's and don'ts. Then only the response reduction factor available in the code can be used. Otherwise, the building will be called code exceeding, and we have to perform a nonlinear analysis to realistically estimate the ductility, and then with the relationship with ductility we can calculate the actual response reduction factor R, which is specified or illustrated in this figure. So in this figure what we see, this blue curve at the top, it is a typical response spectrum. This we are obtaining from either from code for the zone in which my structure is located, or we can perform a site-specific hazard analysis and get this response reduction factor using PSHA or DSHA, probabilistic seismic hazard assessment or deterministic seismic hazard assessment. So this is realistic demand. So demand we get realistic, as close to the reality as possible. Then we divide it by the response reduction factor R in our conventional method, and then we apply certain factors of safety. So actual capacity of my structure is somewhere here. So this is our current code-based method. And those buildings where this method may not be applicable, those conditions I have listed here. So buildings with stiffness and strength irregularities. So different types of stiffness and strength irregularities are listed in the code. So if any of those irregularities is there, then the code-based method is not applicable. In that case, our building is code exceeding, and we have to perform a nonlinear analysis. And there are two types of nonlinear analysis we will discuss. In some cases, a static nonlinear analysis method may be valid, but in many cases, even the static nonlinear analysis method may not be valid, and we have to go for nonlinear dynamic method, or what we call nonlinear time history analysis. Then buildings with torsional irregularity, most common type of irregularity in our buildings, because the code demands that the center of stiffness and center of mass should coincide. But this ideal coincidence is not possible. Code has given certain limits within which it permits the torsional response. But if it is beyond that, then the building is declared irregular or code exceeding. In that case, the code-based method is not applicable. Then the building consisting of new and emerging structural systems and devices. This is a very important reason for performing more sophisticated analysis, because there are a number of new construction methods, materials, techniques, structural systems are coming up. For example, we have this thin shear wall system, My1 system. We have flat slab system, which flat slab is now covered to some extent by the code, but it's largely code exceeding. Then any new type of construction and any new material may come up. And then a number of devices, dampers, base isolators are also coming up, for which the codes are not available. So in that case, we may use the codes of other countries in some cases, but in some cases, the codes of other countries may not also be available. In that case, we have to go for a more detailed analysis. Then super tall buildings, taller than 250 meters. Even if the building is symmetric, regular, but the height is more than 250 meters, then we have to go for a more sophisticated analysis. There are two reasons. One reason is that when the building is super tall, its modal contribution from higher modes increases. That is one reason. Secondly, the damping, the value of damping available in taller buildings is less. And the response reduction factor, which we use in our code, is also observed to be dependent on the period of the structure. So in case of super tall buildings, the period is going to be very long. And in that case, the response reduction factors given in the code are not applicable. And that's why in this case, we have to go for some detailed analysis. And then buildings with special functions and performance objectives can also be categorized in code exceeding buildings. Which type of buildings require better objectives, better performance objectives? Those buildings which have post-earthquake importance. For example, hospital buildings. So the current philosophy of design for hospital buildings is that we use a higher importance factor, 1.5. We increase the forces by 50%. But the question is whether by increasing the design forces by 50%, will this building be operational after earthquake? So the current methodology based on code cannot answer this question. So in that case, we have to go for performance-based design, which is a code exceeding design methodology. So you are familiar with this type of building. These are quite common, even in high seismic zones, zone 4 and 5. So not only in Bombay, and these figures are from, at least one is from Delhi. So there we have quite irregular configurations of the buildings. And their behavior, even linear behavior, is difficult to visualize how these buildings are going to behave during even when there is a small earthquake in which the buildings remain elastic. When the buildings yield, those go in an elastic range, this behavior becomes even more unpredictable, even more challenges to predict. So in such cases, definitely the code-based methodology cannot be used. The simplified linear analysis cannot be used. And the right side building, this is representing a torsional irregularity where large projection is there, but there is hardly any lateral force resisting system to resist that, perhaps to take care of the parking. So this type of scenes are quite common in our urban skyline, and we find many such buildings which are quite abnormal, for which the code-based methodology is not applicable. Then in some cases, the topography, if we are constructing a building on hill, then the foundations are to be kept at different levels, and it gives rise to irregular buildings. So here also, the code-based methodology based on the values of response reduction factors given in the code are not applicable. Then torsion is one of the major regions which which has caused failure during past earthquakes, and all the codes of the world put stringent restrictions on the amount of torsional irregularity which is permitted. Then open ground stories have been observed in Bhuj earthquake and all the earthquakes in the world, where the ground stories which are kept open, those collapse during earthquake due to concentration of the damage. Because when we are talking about the response reduction factor R in our code, it is based on dissipation of energy. And the energy dissipation depends upon how well the damage is distributed in the structure. If the damage is concentrated, for example, in an open ground story, it is concentrated in the ground story. So in that case, the dissipation of energy will not be good. And in that case, the energy dissipated, the total amount of energy dissipated will be much less. And as a result, the effective response reduction factor will be much less than what is given in the code. And we have to estimate that using some nonlinear analysis method. Then in case of torsional irregularity, I want to discuss a little bit because this is also relevant to our conventional design. Actually, there are three issues with torsional irregularity. One is the torsional flexibility. Another is the torsional irregularity, which we can say either mass irregularity or mass eccentricity or stiffness eccentricity. So if there is an eccentricity between the center of mass and center of rigidity, then the structure will be subjected to torsional response. And if the building is having sufficient torsional rigidity, so like the building has stiffness, and stiffness we define as the force required to cause unit displacement. So we have stiffness in the translation direction x and y. In the same way, we can also calculate the stiffness against rotation. So if we take, we apply a moment about vertical axis, a torsional moment, and calculate the rotation, that the moment by rotation will give us the torsional stiffness. So if the building is having adequate torsional stiffness, then even if it is having some eccentricity, its torsional response will be less. But in some cases, even if the building is symmetric, there is no eccentricity, it is symmetric even in both the directions, but its torsional stiffness may be so low that due to some accidental torsion, the response may be so high. In many cases, if you have a square building which is having square columns, so everything perfectly symmetric in both the directions, but it will be torsionally irregular because the torsional response under a small torsional irregularity, which the code specifies in terms of accidental eccentricity, it can undergo large torsional deformations. So that's why the code puts a restriction on torsional flexibility as well. And you may be familiar with this. The code says that the first two modes should not be torsional modes. The torsional mode should be third mode. What does that mean? It means that the stiffness in both the torsional, both the translational modes is higher than the torsional mode. So torsional flexibility is controlled indirectly like that. But the most critical issue is what we call strength eccentricity. If the strength of the members, lateral load resisting members, on one side is much less as compared to the members on the other side of the building, then after yielding, when the members on the weaker side yield, the structure will become highly torsional, highly irregular. So that type of situation is most important, and that cannot be predicted using our normal analysis methods, because there we do not take into account strength. We only take into account stiffness. So our conventional analysis can predict stiffness irregularity or torsion due to flexibility or asymmetry of stiffness and mass, but it cannot predict the torsional response because of the asymmetry of strength. That can come only from nonlinear analysis. And all the codes of the world, that's why put serious restrictions. Then only the codal method is applicable. Otherwise, the building will be considered as code exceeding. Then strength irregularity is another problem. When we talked about open ground story, when we are keeping ground story open for parking, then both the problems are there. It is having a stiffness irregularity. The stiffness of the ground story is less than the stiffness of the upper stories. But more than that, it is the strength irregularity which is causing problem, because the strength of the ground story is much less. When we put masonry infills to our frame, RCC frame, it increases both strength and stiffness. And strength is increased roughly 2.5 times. So the strength of the bottom story, which is open, is 1/2.5 of the strength of the upper stories. And as a result, the damage is concentrated in this story. And if we have to avoid this situation, we have to ensure that the strength of the ground story is higher than the strength of the upper stories. Stiffness also, our code says that we have to match with the upper stories, but more than stiffness, it is strength. And again, strength of a story cannot be predicted by our conventional method. For predicting strength of any story, if I have to estimate strength of the ground story vis-a-vis strength of the upper stories, I have to perform a nonlinear analysis. Then only I can get the estimate of strength, and I can ensure that there is no strength irregularity. Stiffness irregularity I discussed and you are familiar. Then mass irregularity, two types of mass irregularity. One is mass eccentricity, which gives rise to torsion. Another is that the mass, there is a lot of mass concentrated on one story. So when a lot of mass is concentrated in one story, then the dynamic behavior of the building will become irregular. And our normal analysis, especially the static analysis, cannot take care of that. And we have to go for more sophisticated analysis. Then there are several types of in-plane irregularity where a shear wall can be shifted in plane or out of plane, and variety of discontinuities. Floating column is one of the common problems, or what we have the transfer girder in case of the buildings where we have podium. So above the podium, there may be some columns which are starting from the beams. So all those cause irregularity in the building, and that type of buildings cannot be designed using the conventional code methods, using the response reduction factor given in the code, and we need a nonlinear analysis. So the solution, as I'm saying, is nonlinear analysis, and we will talk about this nonlinear analysis. So to summarize the codes, the current codes recommend to avoid irregular. Irregularities are defined in the code, but it is not possible to follow those do's and don'ts of the code in every case. In many cases, those strict guidelines of the code are not specified. And we generally complain that code is too conservative, it is too restrictive, it does not allow any innovation. Well, that's true, but that is because of a reason. And that reason is that code permits such a simplified analysis. So if I want to exceed the code, I can, but then I have to perform a more sophisticated analysis, which should take care of that type of irregularity which I am allowing in my building. Then even perfectly symmetric buildings, as I discussed, may many times come as irregular buildings. So otherwise the building is perfectly symmetric, regular, square. Even then it may be torsionally irregular. So what to do in that case? One way is changing the configuration. We follow the codal provisions, or we perform an analysis taking into account the effect of torsion. Then standard seismic design provisions for regular buildings cannot be used for these irregular buildings, and we have to perform building specific analysis. And special studies are required to predict the response. And we will see when we will be talking about nonlinear analysis that it cannot be done purely numerically. That's the problem with numerical, the nonlinear analysis. Linear analysis or linear behavior of the structures is possible to be simulated using numerical methods. And if we have to perform experiments, those are very simple experiments, like finding the value of E, finding the modulus of elasticity of steel, and so on. So simple test on cubes and rods we can perform, and we can perform the linear analysis. But in case of nonlinear analysis, it is not so simple. The behavior of a member cannot be predicted. The nonlinear behavior of a member or a structure cannot be predicted directly based on the nonlinear behavior of the material. So even if I know the full nonlinear stress strain curve of concrete and steel, I cannot predict the behavior, nonlinear behavior of the member, beam, column, shear wall made of that concrete and steel. I will show you what is the problem there. So experimental results are invariably required. So if that type of experimental information is available from the test somewhere in the world, we are lucky. We can use that. But if I want to use, if I want to promote a new system for which I want to perform nonlinear analysis, then it is necessary that we conduct those tests. We get that data experimentally, and then only we can perform the nonlinear analysis. So that is the biggest hurdle. Nonlinear analysis is possible using desktop exercises. Now computers are also there, but the input required for nonlinear analysis, that comes from experiment. And that is the biggest bottleneck currently in application of nonlinear analysis. So the way forward is this: in all these cases, we have to not only estimate the realistic behavior or realistic demand. This blue curve is the same as we have seen earlier. This is the realistic demand given by the response spectrum. And this brown curve, this is the capacity. So we have to get the capacity also realistically. And here the capacity is not only strength, capacity is not only stiffness, but it is the complete load displacement behavior of the structure. So this load displacement behavior of the structure, we call capacity curve or capacity spectrum. So we have to get a capacity curve or capacity spectrum of my structure, and then I can compare the demand and the capacity, and if that combination of demand and capacity is in a reasonable range, which I have targeted, then the design is acceptable. Otherwise, I have to modify the design of my structure. So one very good reference for nonlinear analysis, because many times people ask which book we should follow for nonlinear analysis, which is the text. So I can say that the best reference available for nonlinear analysis is this AC41 2017. 2017 is the current version, but there are earlier versions also. So this is the most comprehensive document which provides you a lot of information. And this is useful not only for nonlinear analysis, this is very useful even for linear analysis. So I will suggest that we should go through this and have a copy of this. And as you can see in the title, it is seismic evaluation and retrofitting of structures. So all this methodology was developed for evaluation of existing buildings, because when you are constructing new buildings, code can pose some restrictions, do this or don't do this. But when we are evaluating an existing structure, existing building, we do not have that luxury. Whatever way the building has been constructed, regular or irregular, that has been already constructed. And we have to evaluate seismic performance in the of the existing structure, the way, in the manner it has been constructed, it has been designed and built. So that's why this becomes a more versatile method. And this method we can also extend to design of our new buildings if those new buildings are not following the code, if those new buildings are exceeding the code. So same methodology is applicable. So I will focus on only on the analysis method here. I will not talk about the design of retrofit. Okay, so before coming to the actual analysis, let us discuss terminology, which is now quite common, and there is a lot of confusion in our designer fraternity regarding quantification of hazard. So we know earthquake is a rare phenomena. It is quantified in terms of its return period or the probability of accidents. So it is specified as 50% probability of accidents in 50 years, what we call serviceability earthquake. It has a mean return period of roughly 75 years or 72 years. So this is a common earthquake which is expected to occur at least once, 50% probability of occurrence during the lifespan of our structure. Then we have another label which is very commonly used, 10% probability of accidents in 50 years, return period of 475 years, and we call this design basis earthquake, DBE. And another very commonly used the hazard label is this 2% probability in 50 years, which we call maximum considered earthquake, MCE. and it has a return period of roughly 2,500 years, 2,475 years to be more precise. Very commonly you will hear MC and DVE. And one of the questions is that the zone factor Z given in our code, what is that? Is it DVE or MC? So I want to clarify that this is neither DVE nor MC. So this probability of accidents you will get if you perform a probabilistic seismic hazard assessment. Then we will get probability of accidents. But currently the zoning in our code is based upon deterministic seismic hazard assessment, DSHA. And there we have used the mean value. And there is an approximate relationship. It is not a theoretically derived relationship, but a rough approximate relationship is there, that 1.5 times the mean value which you are getting from DSHA is close to MC. So if you take Z from our code, multiply it by 1.5, then it is something close to MCE. So for MC, we should multiply it by 1.5. And you know, the load factor given in our code for earthquake 1.5, actually it is not a load factor. That also causes a lot of confusion. It's more like a correction factor, because what is given in our code, that Z is not dB. If you multiply that by 1.5, then it becomes MC. And dB is, as per our code, roughly half of MC, so MC by 2. So 1.5 Z by 2, that is dBE, and this is equal to 0.75 Z. And then we have the serviceability earthquake, SE, serviceability level here, 50% probability of occurrence in 50 years. That is approximately 1 over 1.5 of dBE. So then you can see this will become equal to Z by 2. So when you are using Z by 2, actually you are getting serviceability earthquake. And that's why those who are involved in design of bridges know that when we are doing serviceability checks in case of bridge design, we are using Z by 2 without any factor of 1.5. But when we multiply 1.5 with Z by 2 as the load factor, then we get dBE. And MC is 1.5 Z. So in our design, we are using actually dBE. It is 1.5 times Z by 2. So we design, when we multiply this by 1.5, then it becomes dBE. So this 1.5 times Z by 2, this we are using. And all our designs are based upon this. And we assume that our structure will survive MC. Although we do not make any check for MCE. All our checks and designs are for dBE in our conventional analysis. But in our performance-based methodology, in our nonlinear analysis, we can estimate performance for any of these levels, any level from here or even beyond that, if I decide any other probability of accidents, because in some cases we use 1% in 50 years. So that corresponds to a return period of 10,000 years. So something like that also we can consider in our design. So now coming to the actual tool, actual method which we can use for analysis of such buildings. This is nonlinear behavior we are trying to predict. So nonlinearity in a structure comes from the material, because the material behavior is nonlinear. Whether we talk about concrete or steel, both have nonlinear stress strain curve. So here we see this smaller curve. This is behavior of unconfined concrete, and this larger curve, this is behavior of confined concrete. So unconfined concrete does not have much ductility, but when we confine it, we get good ductility. And confinement comes from the stirrups. You can see here from the hoops, circular hoops, or from rectangular hoops, and ties, we get the confinement. And once the concrete is confined, we get good ductility. And people have compared different types of arrangements, and what you see here, the maximum ductility or the ductility in our RCC section in bending is depending on how many longitudinal bars we have along the perimeter, which are restrained against movement. So you can see C, the curve C corresponding to this arrangement is giving us the maximum ductility, whereas A is giving us the minimum ductility. Then steel also has ductility, or rather steel has much larger ductility. In case of even confined concrete, we cannot get close to the ductility what we get from steel. So mostly we will depend on steel in our RCC structures for ductility. If we are talking about a steel structure, then of course we have ductile behavior. But when we are talking about steel, then the ductility is derived from, we are talking about RCC, then ductility is derived from steel. In case of steel, you can increase its strength as the grade changes. The strength can be increased by cold working and change in the chemical composition. But there is an issue. As we increase the strength of steel, its ductility decreases. That's why the codes have a limitation on the maximum grade of steel which we can use. Because if we are using very strong steel, then the ductility will be compromised. Then we can analyze a section. I will go a little bit quick here because this is the theoretical background and I want to spend more time on the practical aspects. But if you are interested, we can discuss. So we can analyze the section in the same way as you have done in your RCC design case, RCC design course. So in any section, we first assume a strain profile by Euler hypothesis that the plane sections remain plane. So the strain distribution is linear. And then we get the stress block corresponding to this strain using a stress strain behavior of each material. And we get compressive force and tensile force. And then we equate C equal to T. Then we get the neutral axis depth. Same thing we do here. Only thing is that we add another parameter here, which is curvature. And curvature is given by this angle. So you see this phi, which is the angle made by the strain profile. This angle is curvature. You can show with some geometry that this phi is, this angle is actually second derivative of displacement. So this is del square u by del x square. So that becomes our curvature, and it can be obtained for a section. The curvature can be obtained like this. So this angle also we take, and then we can go on changing the strain profile. We can go on increasing the strain. We will get the corresponding moment and curvature, and we can plot this moment curvature diagram. So in our section, we have used material, concrete and steel, corresponding stress strain curve. So this depends upon the ductility of the material. We obtain the moment curvature diagram. And here you see initially the slope of the moment curvature diagram is very large. It is very steep. And then the slope changes. And then somewhere here, the first steel rod yields. And then there is significant nonlinearity and the slope decreases. It may become even flat. Sometimes it may even become negative. So there may be a strain hardening. There may be elastic plastic behavior, perfectly plastic behavior. There may be strain softening. This slope of this moment curvature curve, this is also very important. M upon phi. You remember, this is nothing but EI. So M upon phi is equal to EI. So this is giving us, the slope of this curve is giving us the effective stiffness of our RCC section, or we call it effective rigidity, EI. Stiffness involves length also. So 12 EI by L cube or 3 EI by L cube is the stiffness, and rigidity is EI. And because the RCC cracks, the concrete cracks in RCC, the rigidity is different than what we obtain based on our gross section. So BD cube by 12 into E, it is different than that. Actually, it is a fraction. And ESC 41 has given this table based on similar analysis that in case of non-pre-stressed beam, it is only 30% of the gross EI. So only 0.3 times. In case of columns, this may vary from 0.3 to 0.7 depending on the axial load. So when the columns have very low axial load, those are behaving same as the beam. And in that case, both the values are same. But when the axial force is large, then the cracking will be less. And we can understand that the effective stiffness is going to be more. So that is going to be 70%. And like that, it is given for all structural components, including shear walls. So this table we can refer from ASC 41, even for our linear analysis, because stiffness is required even for linear analysis. So this effective stiffness we have to use even our linear analysis. And in case of nonlinear analysis, this is even more relevant. Then from the curvature ductility, we can move to the displacement ductility. Simply, if I take a cantilever and a load is acting here, the moment diagram will be linear. And we know the curvature diagram, that will be m upon EI. M upon phi was EI, so m upon EI is phi. So till the steel has yielded, the member has yielded, this will remain a straight line. The phi will also follow the same straight line. And once the yielding occurs, then this relationship between moment and curvature, this will become nonlinear. So we will get this type of a shape. Now what we do, we simplify this curvilinear shape of moment curvature diagram by dividing it into a triangle and a rectangle. And this triangle portion is done such a way that the maximum curvature is equal to phi y. Phi y was our curvature at yield. So it is equal to the yield curvature. And the remaining curvature is the plastic curvature. So this is the ultimate curvature. This is the yield curvature. And the difference of the two is the plastic curvature. And this rectangle, the other side of the rectangle, which is represented by LP, and it is called plastic hinge length. This is obtained in such a way that when you integrate this curvature diagram twice, you know how to obtain displacement from curvature. Curvature is second derivative of the displacement. So the displacement will be 2 times integral, double integral of the curvature. So if we integrate this diagram, then we get the same displacement of the tip as we have obtained experimentally. So this LP, the plastic hinge length, is not obtained theoretically. It is obtained experimentally, empirically, such that the numerically calculated displacement matches with the experimentally obtained displacement. And based upon that, several models are there. One model I have given here, so you can go through this. Then we can convert the moment curvature curve into force displacement curve, because there is a relationship between force and moment, and there is a relationship between curvature and displacement. So I can get a curve here, which is between force and displacement. And this curve we usually represent by an equivalent bilinear idealization. What is this equivalent bilinear idealization? I am representing it by 2 lines. The first line, the inclined line, is passing through the first yield. This was the point where the first steel rod in my beam yielded, in my cantilever being yielded. So I will join this, that will give me the first line, and the second line I will join with the ultimate point in such a way that the area under the 2 curves is same. So this equivalent bilinearization is done to have the same area under the curves. And we are interested in the area because finally we have to estimate the energy dissipated by our structure. And energy dissipation is given by the area under the force displacement curve. So that's why we are interested in the area under these 2 curves. So we obtain this idealized behavior such that the area is matching. And then this point we define as the yield point. And the corresponding displacement we call delta y. So yield displacement is not corresponding to the first yield, where the first rod is yielding. It is where these 2 lines are meeting. So it is a notional point. And the ratio of the maximum displacement, delta u to delta y, we call it displacement ductility mu delta. Okay. So initially we obtained strain ductility or material ductility, which was epsilon u divided by epsilon y for the material. Then we obtained curvature ductility from strain ductility, that is mu phi. Then we obtained rotation ductility, which was theta u by theta y. And then finally we got the displacement ductility. And actually we are interested in this ductility. When I said that R is equal to mu, then I mean displacement ductility, not the rotation ductility or curvature ductility or strain ductility. It is the displacement ductility in which we are interested. So I have to perform analysis, nonlinear analysis of my structure in such a way that I should be able to get its load displacement behavior. And that I obtain by defining the load displacement behavior of individual members. And then I perform an assembly and analyze my structure and get the ductility, displacement ductility. So displacement behavior is to be obtained. Now, to represent displacement, we use another term, what we call chord rotation. So this chord rotation is different than the usual connotation of rotation we have. If you see this fixed column, which is subjected to lateral translation, it will bend in double curvature. And you can see that the rotation is actually continuously changing. At the support where it is fixed, the rotation may be 0, and then the rotation increases, and again it reduces, and then it becomes 0. So the rotation is continuously changing along the elastic curve, along the length of the column. But we define a rotation term which is actually delta by L. So if I join the chord, the two ends of the column, I join by a chord and take rotation of that chord from this initial position, then this rotation is chord rotation. So this chord rotation is expressed in the units of rotation, radian, but actually it is representing displacement. So it is like inter-story drift ratio. So in a column, if the top story is displacing by delta as compared to the bottom story, then the ratio of this delta to h, that will give us this chord rotation. In case of a cantilever, this is given by the displacement of the tip divided by the height of the cantilever. Okay, and this will be delta by 2. So you can see that the chord rotation remains same, because when you divide this into two cantilevers using a point of contraflexure here, you can separate these into two equivalent cantilevers. The amount of curvature, the amount of rotation remains, the total amount of rotation remains same. And that is represented by this chord rotation. So when we will be using rotation in nonlinear analysis, actually we will be referring to chord rotation, not the rotation of the elastic curve. Then there is another problem. That problem comes because of the cyclic nature of earthquake. So what happens when the structure is subjected to a reversible force and the force is small? Then the loading and unloading curves are same. That's how we define the elastic behavior. So in elastic behavior, loading and unloading occurs along the same path. So when loading and unloading is occurring along the same path, whatever work we do while deforming the structure, the same amount of work we get back. While unloading, same amount of energy. But when the structure yields, it goes into an elastic range, and I start unloading it. Then it does not follow the same path. Rather, it follows a path parallel to the original load displacement behavior, original loading behavior. So this path and this path is parallel. And we get this loop under cyclic load, which is close to a parallelogram. And this is called ideal hysteretic behavior, where the loading unloading behavior is such that we get almost a parallelogram shaped hysteretic loop. Another important thing here, that the area of this hysteretic loop is representing the energy dissipated per cycle. So size of this hysteretic loop is very important to us. If my structure is able to dissipate energy at the same rate at which the earthquake is transmitting the energy to my structure, it will be able to survive the earthquake. So the size of this hysteretic loop has to be sufficiently large. How the size of this loop can increase? One way of increasing this size is by increasing the displacement. You can see if the displacement increases, the size of the hysteretic loop increases. So if a structure is subjected to a stronger earthquake, the size of the hysteretic loop will be more, and the displacement to which the structure will be subjected will be more. Only thing we have to ensure is that the maximum displacement which is occurring in my structure should be within its collapse capacity. It should not collapse here. Then it will be able to survive the earthquake. But if it collapses, if this displacement goes beyond the maximum limit, then the structure will collapse. Then let us compare this almost ideal behavior which we get in case of steel with that of reinforced concrete and masonry. Masonry is something like this, whereas it is like this. these three figures I have taken from A.K. Chopra's book. Typical masonry, steel and RCC structures are compared here. And what you will see when you compare this with this, you see here that the amount of force required to cause this displacement in successive cycles is more or less same. There is not much change in the force here. But when you compare it with RCC, what you see here, first cycle force was this much, second cycle the force has reduced, third cycle the force at the same displacement, and fourth cycle the force at the given displacement is even less. This phenomena is called cyclic degradation. And this cyclic degradation gives rise to what we call low cycle fatigue. So you are familiar with the formula of the phenomena of fatigue under working loads. So when a train is passing over the bridge multiple times, every time it is causing some stresses, but those stresses are much less than the yield stress. And that will also cause accumulating damage. The damage get accumulated under each cycle. And actually the structure requires millions of cycles to collapse. But if the same load continues for millions of cycles, it will collapse. But what will happen here? In few cycles, the strength is degrading here because the damage here is much more. We have taken our structure into inelastic range. The strain is much more than the yield strain. And in that case, there will be very rapid deterioration of strength and the structure will collapse under few cycles. This phenomena we call low cycle fatigue. And this is the major region of failure of our RCC or steel elements during earthquake. So in our analysis, we have to take into account this cyclic degradation of strength. Under cyclic load, the strength reduces. Then not only that, you can see that the slope of the load displacement curve is also changing. It's reducing with successive cycles. Whereas here, this was more or less same in all the cycles. But here, this is reducing. This is cyclic degradation of stiffness. So under cyclic load, like earthquake load, there is degradation of stiffness in successive cycles. There is also degradation of strength. So both these cyclic degradation of stiffness and strength should be considered in our analysis. One simple method of considering cyclic degradation of stiffness is given in ASC 41 in terms of what we call backbone curve. So what is this backbone curve? This backbone curve is an envelope of the hysteretic load displacement curve. So hysteretic load displacement curve, which is in the form of loops, if I draw an envelope of that, this behavior I can use in place of monotonic load displacement curve. Monotonic load displacement curve will be somewhere here, which will have higher strength and higher ductility. But because of cyclic degradation, the strength as well as ductility reduces. So if I use this envelope, I can take into account cyclic degradation of strength. But cyclic degradation of stiffness still cannot be taken into account. That can be considered only in case of nonlinear time history analysis, where we define the full hysteretic behavior. So based on this envelope, an idealized shape is given in ASC 41, and ASC 41, this idealized, generalized backbone curve is given like this, where point A is origin, B is representing yielding point, C is the point where there is drastic change in the strength. So what happens if you are thinking of RCC, then what is happening here? This point is where significant yielding. So please remember, this is a notional point. It is not the point where the first yield in the first reinforcement bar occurred. That was first yield. That was occurring somewhere here. So here is the yielding occurring. And then here, the concrete gets crushed. But you will remember, even when the concrete fails in compression, steel is still intact. It has not ruptured. Still, it can take some more moment, some more load due to catenary action. And this is the residual capacity. And finally, here, the steel also ruptures. When the steel bars also rupture, fail, then there is failure. So to define this curve, you need three parameters, A, B, and C. So So using these parameters A, B, and C, you can define. Point B will be given from the linear behavior, because stiffness, you already know, 0.3 times ECIG, and the yield strength you can obtain from the section analysis. So if you know this point A, B, and C, you can complete this backbone curve. And if you are performing a nonlinear analysis, then not only this backbone curve, you have to give the hysteretic model. So there are some hysteretic rules available in literature by which you have to try to simulate the actual behavior. So those rules are specified, and it is a calibrated hysteretic curve. So the blue curve is the idealized one, and the red curve is the experimental curve. Okay, and this is a typical non-ductile frame or non-ductile beam, and this is a ductile beam. And here you see the energy dissipated in successive cycles. So how the cumulative energy dissipated is there. So finally, our objective is to simulate this energy dissipated in the actual structure and in our model. So you can see that these two are quite close. Then there is another model available. This is the so-called lump plasticity model, which is available in SAP and ETABS. So there you can simulate it. If you are interested in learning more than this, then we can have another talk where we will talk about in more detail how we can simulate this. But you can at least try with the existing hysteretic models in SAP and ETABS. Then there is a fiber hinge model also, where you can define the section in terms of fibers. And there also the objective is to simulate this cyclic behavior, cyclic degradation, and the energy dissipated in successive cycles. So the cumulative energy dissipated in successive cycles, that should also be simulated. Then similar hinges we can use in case of shear walls also. And code ASC 41 has given these values of A, B, C. I have not shown here. Similar tables are also given for beams and columns. So you can check these values. You can get these values of A, B, C there. This is for shear wall. So depending upon the amount of the reinforcement and axial force in the shear wall, the shear force, and the boundary elements. So if the boundary elements are properly confined, then this is yes. If the boundary elements are not confined, then this is no. And there is a range of shear force vis-a-vis shear capacity. So based on that range. And here this takes into account the tensile reinforcement, compressive reinforcement, and axial force. So depending on how much compressive action is there, we get the value of A, B, and C. So the value of B is representing the total plastic rotation. So this is representing ductility. And then here you also have the limits corresponding to IO, LS, and CP. And you can see that CP is matching with B. So same value. So CP corresponds to collapse, whereas IO and LSP are smaller than CP. So these are representing better performance than CP. And as the name suggests, IO, immediate occupancy. So this is representing the damage. It will restrict the damage to an extent that the structure will be able to be used immediately after the earthquake. So we can occupy it immediately after the earthquake. Life safety, LS. Here the structure will get damaged, the component will get damaged, but large chunks of material, concrete, will not fall, so that there is no fatal injury. Some injuries may be there, which may require some first aid or some treatment, but life-threatening injuries will not be there. Then another issue while doing our nonlinear and as well as linear modeling is modeling of joints. So many times we ignore the joints, but when we are talking about nonlinear analysis or a displacement-based analysis, then we cannot ignore the joints. So two types of models are possible for modeling the joints. One is what we call explicit joint modeling. In explicit joint modeling, we model the joint using two rigid elements hinged here, and the stiffness of the joint is modeled using spring. But this is a bit cumbersome. So simplified methods are also given in ASC 41, and it says that three possibilities are there. if the column is stronger than the beam, sigma MNC is greater than sigma MNV. So this is the nominal moment capacity of column, nominal moment capacity of the beams. So if the columns are stronger than the beams, then we can take the joint portion of the column as rigid, and the beam portion we can assume to be flexible. On the other hand, if the beam is stronger than the columns, then we can take beam as rigid and column portion as the flexible. If both are comparable within 0.8 to 1.2, then we can take half of the column offset and half of the beam offset as rigid. And these options are available in all our nonlinear analysis software. There you can simulate the stiffness of the joint. Then coming to the main attraction for today's talk, and later on Professor Gadgil, once I finish it, Professor Gadgil will take up a practical example, is this pushover analysis. So what is this pushover analysis? Pushover analysis is the simplest nonlinear analysis method of structures, especially the building frames. And this is also called a nonlinear static method. Why nonlinear static method? Because here we do not consider the dynamic or reversible nature of earthquake. We consider monotonically increasing force in the lateral direction. So we call it a static method. And it is also called single mode method. Why single mode method? Because here we consider this lateral distribution of load along the height of the building in proportion to the fundamental mode. So for performing pushover analysis, we have to consider a base shear, and that base shear is to be distributed along the height. So some distribution along the height I have to take. Now, which distribution I should take? That distribution should be representative of the distribution during earthquake as closely as possible. That means we require analysis of the structure. So it becomes a vicious circle. So the closest approximation to that is the fundamental mode. So we know that fundamental mode in all our normal buildings has more than 75%, 80% contribution. So we can take this proportional to fundamental mode, and we go on increasing this load. I do not know how much load my structure can take. So I will take any arbitrary value of base shear and subject it to this load. And let us make a model, our conventional model, linear elastic analysis, as you do for our normal analysis. If I do that, and then this building will undergo deformation. We will take the maximum displacement at roof, and the base shear. Base shear is representing the total force which is acting on the structure. So total force versus roof displacement, the peak displacement, maximum displacement we take. And if I plot the relationship between them, it will be linear. Why it will be linear? Because my model is linear. So I have made a linear elastic model, so it will be linear. But in reality, if I go on increasing this base shear, this cannot go on increasing. Some of the members somewhere will yield. Now, can we predict which member is going to yield? Yes, we can. That will depend upon the demand to capacity ratio, where the demand will exceed the capacity first. At that location, our member is going to yield. At that location, we are going to have a plastic hinge. So from our analysis, we can calculate demand, moments at different places. From section analysis, we can get the capacity, the moment capacity, and where the demand capacity ratio is maximum, that point I will take as the first hinge. And the corresponding base shear I can get by equating the demand capacity ratio here equal to 1. Okay, so if I equate that equal to 1, I will get the base shear corresponding to the first yield, the first hinge where this plastic hinge is forming. Suppose I have taken a very large value of the base shear, because I do not know, I have taken it arbitrarily. So if I have taken a very large value of this base shear, then my DCR will be very, very large. And when I equate equal to 1, then the base shear will reduce. So I will get the correct value of base shear notwithstanding whatever value I have taken for the initial base shear, that may be very large or very small, doesn't matter. If when I equate the DCR here equal to 1, I will get the correct value of the base shear corresponding to which the first yield is occurring. Now what? When the hinge has formed here, now my structure has changed. I can release here, I can provide a release here and continue my analysis, because rest everywhere it is still linear. So I can apply further base shear, and then again I can calculate moment and capacity. I can calculate DCR, and now the base shear versus roof displacement will be given by another line. So still my structure is linear, so the behavior will be given by a line, but the stiffness will reduce because now a release has been provided. So the stiffness is going to reduce. And if I continue this process, I will get set of these lines with reduced stiffness. Now till when it will continue? What do you think? It will continue till my structure becomes a mechanism. When my structure will become a mechanism, when all the beams develop the plastic hinges and the columns at the base also develop the plastic hinges. Or when the earthquake force is acting on this building, the building is already subjected to gravity load. The vertical load is already there. So due to that, there will be P delta effect. And due to that P delta effect, its stiffness will become negative. So a negative stiffness will indicate that now the collapse has occurred. So I can complete the analysis like that. And when I join these lines like this, okay, this curve, which I have obtained by these successive linear analysis, this we call capacity curve. So this curve is capacity curve, and this is signature of the building. This is characteristic of the building. Like the demand curve, which we discussed earlier, the response spectrum, it is characteristic of the site. It is characteristic of the earthquake. It is not characteristic of the building. In the same way, so far here, we have not used earthquake anywhere. We have used only the properties of building. So this is characteristic of the building. This is signature of the building. Okay. And on this curve, I will each and every point where my members were yielding. And then I know at which location my first member yielded, then at which location my first member crossed the rotation corresponding to IO. And then here, my first member, it may be the same member or it may be a different member, that crossed life safety limit. And then here, the collapse prevention. This collapse prevention can be because one member crossed CP level, means one member collapsed, or the structure collapsed as a whole due to P delta effect. Both ways this collapse can be reached. So this is my capacity curve. This is the nonlinear behavior. This will give me the performances, and this will also give me the ductility. I can bilinearize this, calculate delta U by delta Y, that will give me the ductility capacity. And based on that ductility capacity, I can calculate the maximum value of R, which I can use in my structure. And if I somehow know how much displacement that earthquake is going to cause on my structure, then I will know what will be the performance level of my structure during earthquake. So suppose my earthquake is causing this much displacement. Then I know that the performance here is worse than IO, but better than LS. So we will call it life safety performance level. But if my earthquake is causing this much displacement, that means the life safety is no more valid. It has gone into CP range. And if my displacement is somewhere here, that means my structure has collapsed. My structure will not be able to survive that earthquake. The structure will collapse under that earthquake. Then, in addition to the material nonlinearity, there is also geometric nonlinearity. You are familiar with geometric nonlinearity and P delta effect. So there are options available in all the software to conduct P delta effect. In linear analysis, also P delta effect is important, but it may not be that crucial as it is in case of nonlinear analysis. So in nonlinear analysis, if you do not consider P delta effect, let us say the capacity curve is given something like this. But when you consider P delta effect, the capacity curve will be given like this. So you can see that the strength will reduce significantly. Okay, so here you see the displacement capacity is not going to reduce, but the strength capacity is going to reduce significantly due to period tie fact. And there are different methods of period tie fact. I will not go into these details until unless there is a question. On a practical problem, I have here, this is the building. And in this building, this curve is showing capacity curve without period tie fact, and this is showing curve with period tie fact. You can see even in the linear range, in the elastic range, the stiffness has reduced because of the period tie facts. And here you can see such significant difference in the pushover curve. So period tie facts are very, very important to consider. We cannot simply ignore these while performing nonlinear analysis. Now, that was about the capacity curve, how to estimate the performance of a structure. So for obtaining performance of a structure, there are several methods. And here we are talking about static method only. So in nonlinear static method itself, there are several methods like equivalent linearization or capacity spectrum method. This is commonly used method. We have yield or inelastic spectrum method. We have displacement coefficient method, adaptive pushover, multimodal pushover analysis. The most commonly used are first and third. So you will find options for these two. Sometimes this is also called ATC40 method. The equivalent linearization method is also ATC40 method. And displacement coefficient method is ASC41 method. So just in brief, I will explain. So in capacity spectrum method, this is our demand response spectrum. Here, this increasing branch of response spectrum is not shown, but actually it is response spectrum. And response spectrum is in terms of SA and T. So this is SA versus T, spectral acceleration versus period. Then our capacity, which was given by this curve, the capacity curve. So this is in terms of base shear and roof displacement. So that is SA versus T, this is base shear versus roof displacement. So how to compare those? So to compare these two, the demand and capacity, we have to bring them in a uniform, in identical frame. And that identical reference frame is what we call acceleration displacement response spectrum, ADRS. So we have to convert the capacity curve into ADRS format to get the capacity spectrum. And this is simple transformation. Base shear we convert into SA and roof displacement we convert into SD. And these expressions based upon dynamics are given here. Using these, you can convert base shear at any point into SA at that point and roof displacement at any point into SD at that point. Same thing we do for our demand response spectrum, which was in SA versus T. So this SA also we convert into SA versus SD. And relationship between SA and SD is simple. SD is omega square times SA. And usually this SA is in the units of G and SD is in meters. So we have to convert this into meter per second square by multiplying by G. And omega I can write down as T over 4 pi square. So this SD is T by 4 pi square SA by G. So you can see SD, T and SA. These three are interrelated. So any two I need to know, the third one I can obtain. So here this is in terms of SA versus T. I convert this into SA versus ST. And another interesting thing you will notice here that a constant period line here is vertical because this is representing constant period. But here, if I take T is equal to constant, then this becomes a constant and this becomes equation of y equal to m into x. This is equation of a straight line passing through the origin. So here this inclined line passing through the origin, this is representing constant period. So a period here will be represented by these lines. Here the period was represented by vertical lines. Here period is represented by inclined lines. So now both my demand and capacity are in the same format. I can compare them. there is only one problem, and that problem is that the demand curve is for a given damping. So the response spectrum which is given in our code is for 5% damping, whereas in the capacity curve, the amount of the damping changes because the size of the hysteretic loop is different. As the displacement increasing, the size of the hysteretic loop is increasing, and accordingly the energy dissipated per cycle is increasing. And if I represent this in terms of an equivalent damping, then the damping is also increasing. So I have to ensure that my demand curve and capacity curve should have the same damping, and when those are intersecting, this is giving me the performance during earthquake or the displacement during earthquake. So iteratively we can do that. We can obtain the pushover curve represented by equivalent parallelogram here, and then there is expression for equivalent damping. This is based upon ED over ES naught. ED is the area of this full hysteretic loop, and ES naught is the area of this triangle, which is below the load displacement curve or the secant load displacement curve. So this area, which is under this secant line given by this triangle, this is ES naught, the full is ED. And please note that there is a mistake here. This is actually 1/4 pi. So this is not 1/2 pi, this is 1/4 pi. So this is 1/4 pi ED over ES naught, and we can calculate xi equivalent. And corresponding to xi equivalent, I can calculate a reduction factor. And why that reduction factor? That reduction factor was also given in our earlier code, IS 1893-2002. If you remember, there was a code, there was a table given corresponding to different damping ratios. Now that table has been removed, but we can refer to that old code. That gives this reduction factor. So I have to take a point here, calculate the equivalent damping corresponding to that, then calculate the reduction factor. For that reduction factor, I will plot the reduced demand. And if that reduced demand is intersecting at the same point, that means the point chosen by me was correct performance point, and the corresponding displacement is going to be there in case of earthquake. Now, once I know this performance point, I can decide what is the performance, because somewhere here was IO, somewhere here there was LS, here is CP. So I know that what is the performance of my structure. So this is the linear static method, and nonlinear static method, and this is the simplest method of nonlinear analysis. And we will discuss this with the help of an example also. But this has limitation. What are the limitations? That here we have used a single mode. So it is applicable to only those buildings where the fundamental mode or a single mode has large contribution. At least 75% of the total mass is participated by or contributed by the fundamental mode. Then only it will be applicable. Secondly, it is based upon equivalent single degree freedom system. So it cannot take into account torsion. So if the building is having torsional irregularity, then this will not be valid. In that case, we have to go for nonlinear dynamic analysis or nonlinear time history analysis. There is another method for obtaining performance point, which we also know as displacement coefficient method or SC41 method. So there is an expression given in SC41. You can go through this. I'm not going into these equations, but it is simple. You can use it. I just want to give you some idea about some other topics. Let me see how much time is there. So I have already almost completed my time. So quickly, I will just take 5 to 10 minutes maximum, and I will complete this. So flat slab, you are familiar. Problem with flat slabs is that there is punching shear failure. And we can do nonlinear analysis of flat slabs as well. And for that, we have to make an equivalent frame model. Only issue in case of equivalent frame model of a flat slab and our conventional frame building is that in case of flat slab, we have to use these elements, torsional element. So here, these are the equivalent beams, and equivalent width of these beams you can get. It's available in our code also. It is available in ACI 318. The only addition here is that the beams are not connected to the column directly. Those are not connected here, but those are connected at an offset and through a torsional element. So this torsional element is also important. And here the yielding can occur in this torsional element or in these column strips, or sorry, beams, equivalent beams. So equivalent beams also, there are plastic hinges. There are in the torsional member also, there are possibility of plastic hinges. So this is the frame, equivalent frame model which we have to make. And similar backbone curves in SC41. This table I have taken from SC41. These are available, and we can assign those plastic flat slabs also. If somebody is interested in more detail of this, please write an email to me. I have a presentation on flat slabs alone, where more details I can provide. But flat slabs are also one of the most common code exceeding type, and you can use this table to perform nonlinear analysis. Quickly, I will just give you in 2 minutes some glimpses of nonlinear dynamic or time history analysis. The difference in nonlinear time history analysis is that in place of that pushover load, monotonic load, we are applying earthquake time history. So we should know which time history we have to use. That is the most crucial thing. And secondly, in the plastic hinges, in addition to the backbone curve, which we discussed, which is given in SC41, we have to apply the full hysteretic model. Okay, so the SC41 helps us in obtaining the backbone curve, the envelope of the hysteretic curve, but it does not give us the hysteretic model. So hysteretic model, either you have to choose based on the literature, where several hysteretic models for different types of materials are given, or you have to calibrate it with the experiments done on similar type of construction. So if you have experimental results available with you, you calibrate by modifying the parameters in the hysteretic loop, you calibrate it with the experimental results, as I have shown in the beginning. So these two are the issues. Let us see how to get the time histories corresponding to my site. So here we have to understand two things. When we are performing nonlinear analysis of a multi-story building, there are two issues. One issue is that there is not single mode. When it is a multi-story building, there will be multiple modes. The fundamental mode may contribute much larger as compared to other modes, but other modes are also contributing. And as the height of the building, the period of the building is increasing, the relative contribution of higher modes will go on increasing. That's why super tall buildings we put in code exceeding buildings. And if you see, even for normal buildings in IS 1893, there is a limit up to which we can use static method. As equivalent static method is nothing but single mode method. So beyond that, we have to use multiple modes or a dynamic method. So if I see in response spectrum SA versus T, let us say this was my fundamental mode. In successive modes, the period T2, T3, etc., those will go on reducing. The frequency is increasing, the period is reducing. So T2 we have here, T3 we have here. So suppose T1 is here, T2 is having larger spectral acceleration, T3 may have smaller contribution. But suppose my T1 itself was here, then you can see T2, T3, T4, every mode will have larger spectral acceleration, and there the contribution of higher modes is more. And that's precisely the reason why the taller buildings which have longer periods are having higher participation of the higher modes. Then another issue is that the stiffness of the structure during nonlinear behavior does not remain same. So you see this is that pushover curve, load displacement curve, and initial stiffness is here, and the period which we are getting from eigen problem solution, that period represents the initial period, or it is corresponding to the initial stiffness. But after yielding, the stiffness, the tangent stiffness becomes almost zero, and the secant stiffness is given by this line. So this is considered to be the effective stiffness, and the corresponding period is the effective period. So you can see that effective period goes on increasing, and the maximum value of the effective period will be equal to or will depend on this ductility demand, the maximum ductility demand. Larger the ductility demand, longer will be the period. Lesser will be the stiffness and longer will be the effective period. So the actual period or actual spectral range which is involved in our structure is not only corresponding to T1, but there is a range which is larger than T1 and much smaller than T1. And that's we have to consider while selecting the ground motion. So while selecting the ground motions, we have to select those ground motions in such a way that those ground motions should be able to represent this whole range, not only one point. Those should be able to represent this whole range, and this whole range usually we take from point 2 to point 2t to 3t. So whole of this range, our ground motion, the selected ground motion should be able to consider. So AC7 gives detailed guidelines to select the ground motions for nonlinear time history analysis. And it says that we have to consider at least 11 pairs. Why 11 pairs? Because this curve, this response spectrum corresponding to which we are selecting our time histories is not given by a single time history. And no real time history will be able to give us or will be able to match this response spectrum fully. So one ground motion is never enough. We have to take multiple ground motions, and there is again controversy how many ground motions we have. Earlier they were saying 3, then 7, and now we are talking about 11. So 11 ground motions, that means if we are considering a 3D analysis, then 22 pairs, 11 pairs, that means 22 ground motions. So 22 ground motions we have to consider in our analysis. And these ground motions should be selected in such a way that these should represent the seismotectonic regime, the seismotectonic conditions at my site. What is meant by seismotectonic condition? Two things. One is the source, that means the magnitude of the earthquake which can occur, which is governing my site, that should be represented, and the type of the soil layers at my site, that should be represented. And the ground motions we are taking, it should have magnitude and rupture characteristics similar to what I expect at my site, or which is governing at my site. And then spectral shape should match with the target spectrum, and we cannot match it fully, so it should match in this period range TL to TU, and TL is 0.2 times of our fundamental period, and TU, the upper limit, is 2 times, minimum 2 times. So 0.2 to 2 times we should take. And as I have said earlier, some of the researchers, they talk about 3T, up to 3 times, because it will depend on how much ductility demand is there on our structure. If we are looking for analysis up to collapse, then the TU will be much larger, because there the ductility demand and hence elongation of the period will be much larger. If we are thinking immediate occupancy or life safety, then perhaps enough. And we may not get exactly, even after this, we may not get, even after deciding this range, we may not get enough number, 11 number of time histories. So what we have to do, we have to do scaling, some sort of scaling or spectral matching of our time histories. What is this scaling? 2 types of scaling we do. One is the amplitude scaling, and another is what we call frequency mode scaling. So in amplitude scaling, we multiply the whole time history by a factor, so that the full response spectrum goes up or down. So the dynamic characteristics remain same. The characteristics of the frequency characteristics of the ground motion remain same. Only its amplitude is modified. And this scaling is recommended by the code. The frequency domain scaling, sometimes people modify the frequency itself so that the shape of the response spectrum matches with the target response spectrum. That is not desirable, because that makes our time history unnatural. So we can select the ground motions which are closest to our target response spectrum, and then we can do some amplitude scaling so that I get my ground motions in such a way that the median here you see average of these 11 time histories. So average is very close to my target response spectrum in the range 0.2t to 3t. Okay, so it may not, all the time histories will never match with my response spectrum. I cannot get that type of time history, but I have to get that set of the time histories in such a way that the median value or average value of those is close to my response spectrum. And then I will perform analysis for these 11 time histories, and I will consider, keep in mind, average response, not the peak or maximum response, because you can see some of the time histories are going much beyond the target response spectrum. So their response may be much larger. If my structure is somewhere here, this response may be much larger. So we are not taking the largest response. We are taking average response of 11 time histories. And based on that 11 response of 11 time histories, we can do that. There are some open source software tool also available, like this is one. There are other tools also, Quake Manager, which helps you in selection and scaling of the ground motions. It is available on this website. You may download that, and then you can use it for your nonlinear time history analysis. Okay, so this was the original suit of the ground motion. Here we have scaled it with respect to SAT. So if I scale it corresponding to 1 point, then at this point, all the time histories will give me the same spectral acceleration. But at other points, those may be very different. So this is also one of the methods of scaling, but this is not commonly used because here it is scaling only at 1 point, not at the other points. So what we do, we try to scale it in a range between 0.2t to 3t. Okay, so that's all about the code exceeding buildings and the nonlinear analysis, static and dynamic. And Professor Gadgil will now take up an example of pushover analysis. You can learn there. And in the meantime, I will go through your questions. And once Professor Gadgil completes his example, then together we can take up your questions. Thank you.
Thank you very much, sir. I would request Mr. Jayan Kulkarni to quickly introduce Mr. Professor Gadgil, and then Professor Gadgil will start.
Good evening, everybody. Thank you, Dr. Yogendra Singh, for your marathon lecture. In fact, the complete stuff which you have spectrum, in fact, which you have shown to all of us, is not, the one lecture time was not adequate for that. And normally, normally you like to answer all the questions in between. That also gives time for the viewers to think and act on that. So next, probably we need one more lecture from Dr. Yogendra.
We'll need one full day session.
Full day session, because normally we do that. Okay. So now let's go to Anand. Gadgil Saranchi. Yogendra Singh ke introduction झालेले Gadgil Saranchi. And now next speaker is Professor N.G. Gadgil. He completed his M.Tech from IIT Mumbai. He has more than 40 years of field experience as well as academic experience. I completed my ME in Visitor in 1979 or so, and at that time he joined as a lecturer. So almost all the 40 years I am associated. I don't say associate, but I know him and I have seen all the developments what had been taking place. He has a very rare quality of possessing a strong theoretical background as well as experience of designing several challenging structures. This is very rare. Normally, persons from academics don't get this kind of a chance. He is open to accepting new technologies and new software. I still remember he used to write subroutines and programs in 1980s and 90s, and we used to use his programs when all the sophisticated programs were very costly and not available so easily. He has mastered several new age software. So he's really mastered. If you have any difficulty in STAT, ETAP, SAFE, SAP, everything he knows well, and like a new eager youngster, he has mastered all kinds of software. And today, apart from, he I think retired maybe 8-9 years back, but since then, he had been acting as a consultant to several industry leaders and helping them in solving their problems or helping them in more modeling or various kinds of complex structure with help of different software. So with this brief introduction, I will request Professor Gadgil to take over and start the session.
Sir, you can share your screen.
Oh, yeah. Can you see my screen now?
Yes, it is perfectly visible. You can go ahead.
It's okay. Can you
Yeah.
hear me?
Yes, that's also clear. Please go ahead.
Thank you, Jain Kulkarni, for your generous introduction. And first of all, let me congratulate Professor Yogendra Singh for a beautiful lecture on the concepts involved in the behavior of concrete structures in the nonlinear region. Now, uh, after considering the entire concepts involved in nonlinear analysis, a design engineer is faced with a problem that he has the theory now, and now he wants to implement it on his software or whatever tool available to him. In that respect, the hand calculations are out, and he has to now see what software can handle, what software can help him in understanding the behavior of his structure in the nonlinear region and so on and so on. With that idea in mind, I have now decided to give my presentation considering these points in general. I will have a brief introduction on the contents of the presentation. Then the moment curvature curve and the nonlinear behavior of material is discussed very briefly because Professor Yogendra Singh has given you a detailed presentation. A nonlinear behavior of indeterminate structure is briefly explained as to how the structure responds beyond the elastic limit. The rotation capacity of RC member is then briefly outlined, and then the real topic starts with the option for pushover analysis, because having got a structure, now I want to see how I can carry out the pushover analysis, what options are available for that, and how I can use software for carrying out the pushover analysis. The important steps, items for carrying out the pushover analysis are outlined. Then one problem is solved for a steel frame where the collapse analysis of the steel frame is considered as a preliminary to pushover analysis. Then the pushover analysis of RC frame is considered next. The results obtained in ETABS for the pushover analysis involves ductility factor, so that is indicated and briefly discussed. Then I have two more problems for pushover analysis. One is a real life problem where a large building is considered. Only thing is, it is a very time consuming process. So I have reduced the number of floors and tried to see how the building behaves under the pushover analysis and so on. And lastly, we have the concluding remark. Okay, having considered this outline, now I want to consider the first part of the presentation, that is introduction. So we have basically the reinforced concrete structure, which is generally designed using the elastic analysis theory. So we presume that the structure is going to behave in the elastic region. We have the normal stiffness method and so on to carry out the entire analysis in elastic region only. Having done that, we go to the next stage in the process, that is to design it. But while designing it, we use either load factor or other factors and presume that the structure is designed for much larger moments, 1.5 times or even larger than that. And we further presume that at that level of loading, 1.5 times the elastic analysis, the structure will still remain elastic in the sense the properties of the structure, material properties will still remain the same. So this is a very inconsistent approach. We have our analysis based on elastic theory, while design is based on limit state, and we still assume that it is a elastic analysis or the material properties E value is still as per the elastic behavior. Now, in that case, we say that we are facing our first inconsistency. Secondly, we all know, and from several experiments, people have realized that if at any point the beam is overloaded, not that it immediately leads to collapse of the beam. For example, if at one particular point where you consider the bending moment in the beam, and if at that point the reinforcement is less than the required reinforcement, not that the beam is going to collapse because of the non-linear behavior of the materials involved. The beam at that point might have its steel yielding. The result of that is some inelastic rotation might occur that will transfer the load to some adjacent area where some capacity is available, and so on and so on. In that case, we say that we have to rely on the inelastic behavior which is inherent in reinforced concrete structure. One more thing which has prompted this particular topic for discussion is the clause in IS 13920, the latest detailing code, where it says that if at all you are designing certain special types of structures like flat slab or stress concrete or non-compliant structure, or you can say non-code compliant structure, then the code says that you have to demonstrate by adequate experimentation and by nonlinear dynamic analysis. Now, this is a very vague term, and it is not very clear to a designer that if he at all he designs a structure, then he has to validate his design by carrying out some nonlinear dynamic analysis and so on. And then many parameters are required for carrying out such nonlinear dynamic analysis and so on, about which code has not given enough guidelines, and therefore there is a gray area in the code pertaining to this. Okay. Now let us consider the problem before us, that we have a concrete section which is subjected to some bending moment, and as the load is increased, then we see that the first stage is the concrete starts cracking, so we say that there is a cracking stage. Thereafter, the linear behavior continues until we get a stage where steel starts yielding. So we have the yielding state, and thereafter, after yielding, the steel goes on elongating or goes on developing large amount of strain without causing loss of stress over there. The result of that is the steel is able to take the same moment. Only thing is it is going to deform more and more, and so on and so on. Now, with this behavior, idealized behavior is generated by the researchers, and that is bilinear curve over here. That is, we presume that until some level over here, the behavior is linear, and thereafter it is almost flat, in the sense that the moment is going to remain the same. Only thing is, no further capacity is available at that point as far as the resistance to moment is concerned. The rotation can occur at that point, resulting into large deformation, and maybe some distribution might occur in the reinforced concrete. The stress strain or the strain diagrams corresponding to these stages are also well known, and we will not discuss in detail this behavior. Only thing is, we will say that when the yielding occurs for reinforcement, then the moment at yield point is the tensile force multiplied by, now we say, the lever arm which is available, and until then we our assumption of plane section before bending remain plane, after bending that holds, and accordingly we have the linear stress strain or stress diagram. Accordingly, we have the lever arm which is 2/3 from this point, and accordingly we have got now the entire lever arm indicated over here, giving rise to the moment at that particular point, and the curvature at that point, which is the rate of change of strain, which is the strain at that particular point, which is epsilon y upon this particular distance, and that is d minus kd. Okay. So now we say that we have got the curvature at that particular point, which is the yield curvature. Similarly, at failure, we get a curvature which is the ultimate curvature, which is also the strain at that particular point, and the distance of the neutral axis from that particular point. So that is now indicated over here as psi u, which is now the strain in concrete over here, and the distance between the extreme compression fiber to the neutral axis. So that is now C. Accordingly, we get the curvature at ultimate. Now let us see how a simple continuous beam is going to behave when it gets overloaded. So we have this simple problem of a two-span continuous beam carrying lateral load. At that particular point, we expect a large moment under the load and maybe not so large moment at the support itself. At this point, now the capacity of the member to carry so much moment is not there. So what is going to happen is, at the point where the capacity is exceeded, the beam is going to develop some non-linear behavior, in the sense the steel might yield and the moment will remain frozen at a lower value rather than the calculated value at this particular point. The result of that is, at that point the capacity is only 0.15 over here, PL upon EI, while the elastic analysis would give us a moment which is 0.24 and so slightly larger than that. But because the beam cannot take it, it will have only that much moment, lesser moment, and at the other point where its capacity is still not yet exhausted, it will go on causing redistribution. The result of that is, at this particular point, the moment would start increasing, and a stage will be reached when at this point also the capacity of the beam is now reached at, for moment. So we have our moment capacity reached at this point, where earlier the moment was less, while at this particular point the capacity was already reached. So we see that in a simple beam like this, where we have a two-span continuous beam, two hinges get formed, plastic hinges, one over here and the other at the support, and accordingly now we have got a full utilization of the structure in the inelastic region over here. Okay. Now, having considered that, we have to see whether the reinforced concrete member has got that capacity to undergo the rotation. If that capacity to undergo rotation is not there, then we don't have any use of that non-linear behavior. Now, over the period, extensive research has been done in this particular field, and people have finally given some empirical formula to determine the ultimate flexural strain and plastic hinge, which depends upon the width of the beam, the strain at failure, and the moment gradient, which is the value given by the distance between the maximum moment and the zero moment, and additional compression steel that we are providing, that is a steel which is always provided at the other end, and of course the confining steel, and so on and so on. So all of that put together is given in terms of a formula. Accordingly, we can see as to how much ultimate strain is available at a particular point, and accordingly what is the ultimate curvature, and finally the rotation that the beam can undergo. Okay. Now that is as far as the general behavior of the material is concerned. Now let us see that, having got all this theoretical knowledge, I want to now carry out the pushover analysis. For pushover analysis, we have got basically three options. One is you apply some load, as Professor Yogendra Singh has indicated, that you can calculate in some way the force to be applied at each of the floor level. Either it can be linearly increased from bottom to top, or it can take the shape of a first mode over there, and so on and so forth. So some kind of distribution you can consider and say that that is the type of load that you want to now increase indefinitely by a multiplying factor, and finally see as to how the structure performs in the inelastic region or so that is as far as the incremental loading is concerned. Sometimes you are required to carry out the pushover analysis by taking displacement as a criteria. So you can say that you have got structure of some height. Okay. Now you want to push the structure by some amount at the topmost point. And for that push, I want to see whether the structure is going to perform properly in the inelastic region and so on. So that is the incremental displacement. So you decide as to how much the deflection the structure is going to undergo under the worst earthquake, and accordingly try to see as to after giving that displacement how the structure behaves and can it withstand that much displacement and so on and so on. And the third one, which Professor Yogendra Singh has indicated, that you have the ground motion. So you can select some ground motion, either the past records or the artificially generated records, and then use that particular ground motion as an input, carry out either the time history analysis or convert that into a response spectrum and use that response spectrum with a multiplying factor to finally generate the behavior of the structure in the nonlinear. So we see that we have three different options of applying the load. Namely, we have the incremental load, or we have the incremental displacement, or we have the incremental ground motion. Okay, fine. Now we see that we have got all these tools ready. We have the software, and now we say that to use the software, now we have to see how to go about the entire process. First thing is you need the ETAB software with ultimate version. Now that is very important because most of us are using normal ETABs, nonlinear analysis. This ultimate version is different. It is quite costly and you need to get that ultimate version before you carry out this pushover analysis. So it is not part of our normal ETAB software. You need to get the higher version of that, the ultimate ETABs version of. Okay. Now, having got that software, then we see that we have to prepare our model in the usual way. Okay. So you have got your model with some gravity loads, seismic load that you have already considered, wind loads and so on. And then you design the structure in the usual way. You have the entire structure designed for the normal loads which you otherwise considered. Forget the pushover analysis. It is the normal design that you are carrying out. Okay. Now, having got this design ready, that is you have designed the structure for the seismic, wind loads, all the loading combinations and so on. And now you want to check its performance because while designing the structure, you are using one important factor which is R, the response reduction factor. So that can be 4, 5 and so on. To that extent, you are reducing the seismic load and accordingly designing your structure. But now I want to see as to under severe earthquake, how my structure is going to behave. And for that purpose, I am carrying out the pushover analysis over here. That is, I want to now apply a larger lateral load, either directly as a load or as a displacement and so on and so forth. Okay. Now I consider the behavior of the structure in two parts. One, I will say that I have already got the gravity load, fine. And now I want to apply lateral disturbance to it and then see how the structure is going to behave, how it is going to resist that additional deflection, and whether can it remain intact or can it survive that large deflection and so on and so on. Okay. So now we have got gravity loads which are there right from the beginning. Now that gravity load analysis might also involve nonlinear behavior. So we will consider gravity load case also as a nonlinear static case. And for pushover analysis, I will consider either the deflection or the lateral load or the ground motion and accordingly apply this lateral disturbance and then see how I can consider the response of the structure subjected to that load. Now, when I apply this pushover analysis, then we will say that under a load pattern and under a load case, I have to define those activities in a specific manner as per the ETAB, you can say regulations, and accordingly consider the entire analysis in that fashion. Okay. Now we say that as far as the entire operation is concerned, we have got the loads to be defined in this particular way. So you can apply incremental load or incremental deflection. Thereafter, you have to consider the structure in the nonlinear region, in the sense we want to now allow some hinges to be formed depending upon the moments developed at that particular section and the reinforcement that you have provided. If you have already designed the structure for the gravity loads, the seismic loads, and so on, you have got the reinforcement ready. With that reinforcement, now you define as to at what location you want the hinges to get formed in case of exceeding the moment capacity at that particular point. Accordingly, we have got three class of members over here. One, we have got beams, where the moment will be the criteria to see whether hinge is formed or not. As far as columns are concerned, we will have axial force and bending moment, either uniaxial or biaxial, to see whether the moment is or the hinge is formed at that particular point. Similarly, for shear wall also, the ETABS has got a criteria as to how you can define, that is under axial load and moment, how you can locate as to the points where hinges are formed and so on. So having considered this basic understanding, now we assign the locations of the points where hinges can form, not that they will form, but can form. That is either at 5% from one end or 95%, that is 5% at the other end. So at that distance from the ends, we will say that okay, the hinges can get formed, that is at the ends of the member, but very close to the end of the member and so on. So we say that these nonlinear hinges are now introduced as a location at those particular points, and then we then carry out the analysis of the structure with only two loading cases to be considered. One is a gravity load under nonlinear conditions, and pushover analysis also under nonlinear conditions. If at all you are considering three-dimensional structure, which is generally the case, you can consider the pushover analysis in X direction or that in Y direction and so on and so forth. Okay. Now, having considered the basic outline, now let us see how we can go about in carrying out the pushover analysis of this simple steel frame. I have considered to start with a very simple analysis where it is like a collapse load analysis of a steel frame. Whether it is a steel frame or concrete frame, we presume that the rotation capacity at the plastic hinges is adequate, and the rotation is possible at those particular points. I have considered this plane frame with the columns of ISMG 400 and the beam of ISW 550. Okay. With these displacements, with these sections, now I am considering the pushover analysis over here. So first of all, we consider the mass source for considering the lateral deflection over here. And for that mass source, we have got either the dead load, the lying load, and so on in the usual way that you have already got as part of your first analysis that you have carried out. Then we have the load pattern, which involves the dead load, which can have several items, or you will have the live load, and then you have the pushover analysis. For pushover analysis, we have got description as other category. Under the type, you have got several categories. Out of that, other is reserved for pushover analysis only. So we say that we have got the load pattern defining the three basic cases: dead load, live load, and push X over here. Then we have the load case definition, which involves dead load, live load, push X, which are already there in load pattern. And now we have got this one more case, which is gravity load case, which is in fact the summation of dead and live over there. So we take the gravity case as also a nonlinear case, and then consider the pushover analysis along with that. And for these two cases, we will just see how the structure performs and so on and so forth. Okay. Now for gravity case, now we consider the further description, we have got a gravity case defined as a non-linear static case, the mass source which we have already defined earlier, and for gravity load, we have got dead load with whatever load factor that you want to consider, and live load also with whatever the load factor that you want to consider. So that is as far as the gravity is concerned, where we say that gravity load is made up of the dead load and live load. Okay, that is all to be considered as far as gravity load is concerned. For pushover analysis, we again consider it as a non-linear static case. We have got the mass source in the usual way. And for pushover analysis, we say that it should consider its effect after the effect of gravity load. So we say that continue from the state at the end of the non-linear case of gravity case. So at the end of gravity case, I will consider the effect of this pushover analysis, which can be either loads, lateral load incremental, or lateral deflection as incremental, or ground motion, whatever is the case. And then I will consider the load applied in terms of the acceleration in x direction, and with appropriate scale factor, I will consider. Having considered that, the next is I want to define as to how I am applying the load, whether I am applying a displacement or whether I am applying a lateral load, and so on and so forth. For that purpose, I have got the next screen, and that is over here. So I will say that I am applying a displacement control over here. So I am considering the displacement control. I am just saying as to how much target displacement I have in mind. In the present case, I have taken 500 millimeter as the target displacement, and at what point that displacement is to be applied. So I am considering it as story at the top of the first story, and the joint number at that point is 1, and the deflection is in degree of freedom u1 at that particular point. Okay. Having considered that, the next thing is the second option at this point, which is the result saved, that is for the second one over here, and that is now indicated at this point, and that is in multiple state I want to save the results. Minimum number of saved states are 20, and the maximum number of saved states are 100. That is all the iteration that it is going to perform, and so many results will be saved in terms of the steps and so on and so forth. Okay. Having considered that, now we say that the next task is to assign the locations of the hinges. So we first of all consider the beams in the given structure, give the location of the hinges at 5% from one end and 5% from the other end, that is 95% from this end. So we define these two locations of the hinges, and because this is a beam, we consider that the hinge is only due to the moment M3. Okay. Similarly, now we have got the similar assignment given to the columns, given to the shear wall. In the present case, we have only the columns, so similar definition is introduced for columns with hinges under the combined action of axial load and moment and so on. Okay. Now we consider the cases to be run, that is set the cases to be run. One is for pushover analysis, now that is nonlinear static. There we say that case must be considered. Similarly, gravity case must be considered also. While other cases like the modal, the dead, the live, and so on, they are not to be considered, because we are now considering only the effect of pushover analysis, where the effect of the lateral deflection is considered after the gravity analysis is complete, and so on and so forth. Okay. So having done that, now we consider the analysis at this particular stage. And for that analysis, now I will just show you the basic, you can see the basic model over here. And for that purpose, now we consider the post-analysis scenario, where we say that we have got the structure which is fully analyzed, and now we now say that, okay, apply. So for that purpose, now we say that after having considered, say for example, this is my first step. In first step, a small hinge is formed, but that is also in a very low region in this particular case, because the full plastic region is developed when you consider the red color at that particular point, where it has reached the yield stress and gone beyond it. So as you consider the next time step over here, then we say that for the next time step over here, now I have considered the next time step, you will see that some more overstressing has occurred at this point and so on. So I will continue with this, more and more hinges are formed over here. And then at the end, now we see that we have got these pink color hinges are formed, which is very close to the yielding and so on. And if I continue further, then we see that at the last time step, which is the 12th time step, now we see that at that point, a deflection of 96 millimeter has occurred and the hinges are formed at this particular point. If you consider another output which is generated by the ETAB, then we see over here the output generated by ETABs in terms of monitor deflection versus the base shear. So we see that to start with, we have got linear behavior, then some hinges are formed, so more and more deflections are taking place. Thereafter, so many hinges are formed, so there is a drop in the load carrying capacity of the section of the structure, and then some strain hardening occurs, further redistribution occurs, and so on and so forth. So we have got the maximum shear applied at that particular point as about 40 kilonewtons, and at that point, the maximum deflection that we see over here is about 100 or 98, and so on. So we see that this is the way we consider the behavior of the structure as is generated by ETAB. In addition to that, ETAB generates one more response diagram over here in terms of a behavior of the structure, where the response spectrum and the you can say the capacity curve, they are all drawn together. One thing is to be understood that as yielding occurs at more and more locations, the structure becomes more flexible. So initially the structure had some period of vibration. Now after yielding at several locations, the period of vibration.
Your slides I think are stuck. They are not moving.
Slide what?
Slides are not moving, I think. Slides you are stuck.
Okay. Can you see screen?
Yeah, screen is seen, but it is I think is stuck. Freeze that one location. Slide number 25, it's clear. So just make it. Your presentation slide number 25 is there still. Further, it has not gone.
This one.
Okay. Correct. Now it is. So it is not moving. I think you are.
Okay. Now, no, it was not moving because I have brought some other images over there.
Correct.
Okay. So now we see that we have got the load deflection curve over here. That is base shear versus the monitor deflection, and so on and so forth. The whole thing is also presented in the form of a table where at each step the code is indicating as to what was the base force and what is the monitor deflection, and so on and so forth. So the entire data is available at this particular point. Further, the period of vibration for each of the time step. Initially, when no yielding has occurred, the structure was very stiff, so period of vibration was very low, 0.087. Later on, when several hinges were formed, the period is increased to 0.386. Structure has become more flexible, and so on and so forth. So we now see that the entire operation is carried out internally by ETABs, and for that particular incremental displacement, the structure has carried out and the software has carried out the entire calculations and given you the deflection at different stages, the force developed, and so on and so forth. One more thing is to be seen at this particular point when you are considering that lemma 440 curve. Here we see that apart from the period of vibration over here, they are giving you the ductility ratio also. Now this ductility ratio, as you have seen some time back, that it is the ratio of the deflection under consideration at ultimate state upon the deflection when the first hinges occur. So we have the structure when first hinges occur, and later on as the more and more deflection is occurring and more yielding occurs, then we see that the deflection keeps on increasing indefinitely, and that ratio in this particular case is the steel structure, so it has got a large ductility. Here we see that the ductility ratio is as high as 19 and so on. So for our structure, we can just see as to can we have large amount of ductility, because larger the amount of ductility you have, larger the energy absorption capacity the structure has got. Accordingly, it has got a better chance of survival and so on and so forth. Okay. The next problem that is considered is this 5-story portal frame, which is subjected to lateral load, which is different than the case that we have considered earlier. Earlier, we had considered lateral deflection. Now, I am considering a uniform lateral force applied, 10 kilonewton at each floor level, and so on and so forth. Now, with that case in as a data, now the analysis is carried out in the same way. The only change was the lateral deflection that is replaced by lateral force. There is no other change. The structure is different, but the steps for feeding the data remain the same. And with this, for the last time step, we see that several hinges are formed at this point. And as far as the behavior of the structure or other response parameters are concerned, we can see the bending moments at these locations over here. So for the last time step or for every time step, you can just get the bending moments and see as to how the structure is now responding, developing internal forces and so on and so forth. So we can see at this particular stage that whether you are applying lateral deflection or lateral load, the ETA does the internal calculations in the usual way, depending upon the data that you have got. And accordingly, it will generate the response in the inelastic region and will give you the desired parameters in terms of ductility factor or in terms of the maximum load carrying capacity and so on and so forth. Okay. And this is of course the FIMA 440 curve, which also indicates at this particular point that at this stage the ductility factor is about 5.9 for this reinforced concrete frame. Okay. The period of vibration also is now changed 1.395 at this particular point because several hinges were formed and accordingly the structure has become more flexible and so on and so forth. Okay. The third problem considered was a space frame, where the space frame is the most elementary space frame, which has got 4 columns and a slab at the top. And for this space frame, again a lateral deflection is considered. For that lateral deflection, the hinge pattern is seen over here. You can see after maybe 12 or 14 time steps, you have got the hinges formed at the base of the column. Some hinges are formed at the top. Now this is a peculiar structure because you have got a slab which is quite flexible compared to the columns, and accordingly the hinges are formed only at the base. Major hinges are formed at the base. At the top, the moment is much less, and so on and so on. And the last problem which now I have considered is a 3-story frame. In reality, this structure is quite big. It is actually a 22-story structure, but the time required for analyzing 22-story may run into maybe weeks or months. It is not very clear. On my computer, it might have taken months for carrying out the full pushover analysis. So I have reduced the number of floors and tried to see as to how the structure responds for the lateral deflections and so on and so forth. So I have got several shear walls in this particular structure. There are several beams, slabs, and so on and so forth. And those structural components are shown over here. The steps involved are the same. The lateral deflection is controlled and the structure is analyzed for that lateral deflection with capacity for development of hinges introduced for shear walls, for beams, and so on and so forth. And after several time steps, after carrying out the analysis in the usual way, now we see that several hinges are formed for this particular structure. Those circles that you see, field of circles, now they are the hinges. So this structure has developed several hinges at the end of 10 time steps and so on and so forth. So we can see that for any structure that you have in mind, for example, over here, if you consider this particular structure, in the usual way, then we see that for this particular structure, I am now considering the response over here. So I am now considering the response of the structure at this particular point. So if you consider the live development of the hinges at this particular point, then you will see that as you consider next time steps and so on, then more and more hinges are formed one by one over here, and then you will know as to at which point the first hinge is formed, and if at all you want to take corrective action, then accordingly you can have your design changed in such a way that that hinge formation gets delayed, and you will have more reserve strength in this particular structure and so on. So to start with, we can say that we have got only few hinges are formed. Later on, with more and more deflection occurring, more and more hinges are formed in the given structure. And finally, at the end of the desired time step, you have got the maximum deflection, and accordingly, you will be able to consider for that particular structure the complete response in the usual way for the given structure. So here we see that we have got again the monitor deflection versus base shear. The maximum lateral force was 54 kilonewton, and the maximum deflection was about 140 or so millimeter. And in the same way, we can consider for this given structure the uh, ductility factor over here. So accordingly, we can say that as far as the ductility factor is concerned, then at any point we will be able to consider the ductility factor over here, and the ductility ratio at this particular point, you can have a look at that, is about 8.57, while the period of vibration is also changed to 0.425 and so on and so on. So we can see that ETAB gives you the complete picture of your structure under the influence of the lateral disturbance that you are considering over here. Okay. Now, having considered these four problems, we see that we are in a position to have a tool which is very powerful. It can consider the given structure, its inelastic behavior, and predict the response of the structure subjected to that lateral disturbance and so on. Only thing is now you will require ETABs with that ultimate option over there. Then as far as the entire results are concerned, we will say that it gives you at each time step where the hinges are formed. So you can gather that information, and if at all you want to monitor or you want to play positively, then you can change the reinforcement at those specific locations and delay the formation of the hinges in case you desire that, and so on and so forth. The ductility factor also can be obtained in the process, and you can see for the given structure as to at different stages of loading how the ductility factor also changes accordingly, and so on and so forth. And accordingly, you can consider active control on the given structure, and at each stage you decide whether you accept the formation of hinge at this location. If you don't want that, you change the moment carrying capacity of that section by providing either a different section or by providing different reinforcement, and so on and so forth. Okay. If at all you want to use this entire operation in a rational way, then you will see that at several places in the given structure, the hinges are not formed at all, which means they have got enough reserve resistance. And if at all you want to encash that, then you can change the reinforcement at those locations or change the section and effectively make the structure more economical, and so on. I think with this, I come to the end of my presentation, and I must say that I am thankful to you all for patiently listening to my presentation. And I hope that with this presentation, you get enough confidence to finally go for the pushover analysis of your own structure and understand your own structure in the inelastic region and effectively use that information to make your design more rational and so. Thank you.
Thank you very much, sir. We have almost about 100 questions. Now, I don't think we will be able to take all, but I will request Dr. Yogendra Singh to have to answer select important questions. I'm sure he must have gone through the list actually. So, can you see the list here? Okay.
Yeah, I was going through the questions, so
Yeah.
I can make out some
Yeah.
groups in which
Correct.
the questions have been asked. So except one or two questions, all the questions were clear to me, but one or two questions I could not make out the context, that in what context they were asking. So I will answer first the general questions. So one question people are asking is that can we use pushover analysis if the fundamental mode is having participation less than 75%? So the answer is no. Pushover analysis is not applicable for structures having fundamental mode mass participation less than 75%. And actually, that is the reason there is a lot of uncertainty or variability in the answers, the displacement we will get from pushover analysis.
Anand, you share the screen afterwards, because unnecessary it is.
Yeah, at the moment, let's keep it open. So this pushover method, unfortunately, before we started doing it, it has become obsolete. And now everybody is talking about time history analysis only. So maybe we have to learn time history analysis directly. But pushover method nevertheless gives a lot of insight. Somebody has commented that also, that pushover analysis can be used to get how the hinges are forming, what is the hierarchy of strength in different modes. So that type of information is there. So pushover analysis is more for understanding the behavior of the structure. But it is not considered to be very precise method of obtaining response, particularly because it has the same limitation as we started with. It is not applicable for irregular buildings. So it is applicable for regular buildings only, because there only you will have 75% mass participation. And it is not applicable for tall buildings, because there also it will be difficult to get 75% mass participation. For torsionally irregular buildings, it is not applicable again. So the solution now becomes nonlinear time history analysis. So we have to learn how to do nonlinear time history analysis. Then the question people have raised that how to get hysteretic model for time history analysis. Yes, that's an issue. So far, no code is available which gives us how to assign nonlinear time, this hysteretic model for RCC or steel elements. So that we have to learn based on the research papers only. So currently it has not come to the domain of design codes. In the design codes, we can develop only the backbone curve, that is the envelope function of the pushover. And one more question is regarding pre-stressed members. So somebody has explained in detail that what happens in pre-stressed members, and there is no rigid ductility available in the pre-stressing tendons. So yes, pre-stressed members do not have much ductility, and that's why we have to be very careful while doing seismic design using pre-stressed members. We can allow pre-stressing only in those components where we are not expecting yielding. For example, slab. So slab is not expected to yield. Slab is not expected to dissipate energy during earthquake. So there we can go for pre-stressing. But or we are designing a bridge, because in case of a bridge, superstructure is not dissipating the energy. It is the column, the pier, which is dissipating the energy. So we cannot have pre-stressed piers, but we can have pre-stressed superstructure because there the role reverses. In case of a building, it is the beam which is dissipating the energy. In case of bridge, it is the column, the pier, which is dissipating the energy. So pre-stressed members are not fit for dissipating energy, and that we have to avoid. Then let me just go one by one now. There is one question related to baffle slab fire safety. I think Mr. Parulekar or Mr. Kulkarni will be in a better position to give that. That can we use 125 mm thickness for fire resistance, 2 hour fire resistance? I have no idea.
Provided you satisfy the cover thickness criteria, you can use, but I don't think you will be able to satisfy the cover criteria by 125.
Okay, and there are a lot of questions regarding whether this PPT will be available or not, or whether the video will be available or not. So we want to clarify that the PDF will be available to everybody, and the video recording will also be available. So you can use it as many times as you want. One question is regarding the time period. Why the time period of the bare frame structure is low compared to shear wall structures? Actually, it should not be. So if you see the period of the formula given in code, the formula sometimes gives you the period of the bare frame lower than the period of the shear wall, but there is a correction. There is a lower bound and upper bound. So the formula which we are having for shear wall buildings should give us the period shorter than bare frame and larger than infill frame, 0.09 hy square root t. So it should be in between only. So if it is giving us longer than bare frame, then we should use bare frame formula. If it is giving us shorter than infill frame, then we should use infill formula. So capping and flooring is there. Yeah, somebody has correctly pointed out when I said that the response reduction factor is the ratio between elastic force and the yield force. Actually, I wanted to simplify the thing. I did not want to confuse you at that time, but it is more correct to say that that is what we call R omega or R mu, sorry, the response reduction factor due to ductility. The response reduction factor which is given in the codes takes into account the effect of ductility, the effect of overstrength, and also the effect of damping, because the response spectrum which we are using is corresponding to 5% damping only. So response reduction factor takes into account the other facts also. So it is not directly equal to mu. So if we have to get response reduction factor for a practical building from the ductility ratio, then we have to take into account the effect of overstrength and damping as well. Okay, this is the most interesting thing, that why response reduction factor is different in different codes for same type of LLRS. So the answer to that is in the origin of these response reduction factors, how these response reduction factors have been obtained. So these response reduction factors have neither been obtained experimentally, nor these have been obtained from analysis. These are based upon the judgment of the code committee. And you will agree that the judgment of different committees may be different. So it is based upon their personal experience and not of individuals, but of the whole group of the code committee. And that's why these are different in different codes. Then, well, there is no definition, fixed definition of tall building that our code says. Our tall building code defines tall building and super tall buildings. Yeah. But theoretically, it's not possible. It's only a relative term. Which is taller than short is tall. As per 1670, there is a definition. There is a definition, 50 meter and 150 meter. So that definition we can use. Now, this question is not entirely clear to me, but I can guess it is about the design of a small 1 meter link beam. So perhaps the person who has written this question is trying to ask Mr. Kiran Kumar Joshi. So perhaps he want to know regarding the link beam in coupled shear walls. So that's what, that 1 meter link beam. So any coupled beam is to be, if we want to make use of it, see, the coupled beam has a very important role. The ductility capacity of coupled shear wall is much larger than a single shear wall. And that energy dissipation comes from the coupling beam. So coupling beam is subjected to very large shear force. So we should design and detail this coupling beam very carefully. If you don't want to design it, write in the specifications on the drawings that this beam is going to fail during earthquake. Building will not collapse, but the beam will fail. And you cannot support anything on this beam. In that case, it can do. But if anything is supported on that, that is going to collapse during earthquake.
That's what he has written. If we make sure that failure of these beams doesn't have failure of gravity load system, then
we can avoid. I mean, then in that case, after this phase, then the shear walls will become independent shear walls, and those will behave like that. So it will not lead to failure of the building, but it will definitely lose the advantage of coupled shear wall. Okay, then there is a question that why only Indian code restricts first two modes should not be torsional mode. No, it's not only Indian code. All codes say that, but the way of restricting it is different. For example, if you see Eurocode, it puts a limit on E by R. So that is another way of ensuring that the building is not torsionally flexible. So this is a simplified way which most of our designers can understand. That's why our code has said. So don't think that this restriction is culprit. This is to make your life simple. Otherwise, you have to do more complex analysis if you don't do that. So this is to save you from more detailed analysis. So otherwise, you have to calculate E and R. R is the torsional radius of the building, for which you have to calculate K theta, and so it will become quite involved. So to avoid that, our code has taken a simpler method that if the torsional mode is not first or second mode, then we will assume that building is not torsionally flexible. Post tension I discussed. Okay, then there is a question regarding reliability of performance-based design. Okay, so we know in engineering, no method is 100% reliable. Every method has some uncertainty. Seismic response estimation has a lot of uncertainty because there is uncertainty in the ground motion, there is uncertainty in the member dimensions, there is uncertainty in material behavior, especially when we are talking about cyclic behavior. So cyclic behavior of material is very, very uncertain. Then our models are also not perfect. So there is a lot of uncertainty. But I can say one thing, that the uncertainty in nonlinear analysis is definitely less than uncertainty in linear analysis. So when we are using linear analysis to predict the response of a seismic response of a structure, then nonlinear analysis has less uncertainty as compared to that. So we can have a better estimate of performance using nonlinear analysis. But definitely it is not perfect. And every day people are working to improve it. Oh, yes, this is one. In case of hilly buildings, it is required to insert torsional hinges. And there was another question related to this, that where to put hinges in our structure. So we have to assign hinges. The computer software cannot decide where the hinges to be provided. So the hinges are to be provided at every point where you suspect or expect the yielding to occur. Okay, so if you assign hinges at more points, there is no problem. If you assign hinge at a point and that point does not yield, no problem. But if you do not assign hinge at a point where yielding should occur, then your results will be erroneous. So it is always better to assign more number of hinges. But what is the problem? More will be the number of hinges, more time the software will take to analyze the model. So we try to provide hinges at those locations where we are expecting yielding to occur. And which are those locations? In case of buildings, those locations are in the beams and columns near the joint. So you should assign hinges in beams and columns, M2 or M3 hinges in beams, depending on what is your axis 2 and 3, and PM2, M3 hinges in the columns near the joints. Then if there is a possibility of failure in torsion of the member, here we are talking about torsion of the member, not the torsion of the building. So when you are talking about a hill building, there is torsion in the building, but torsion in the building doesn't mean that there will be torsion in the excessive torsion in the columns also. So torsional hinge may not be necessary in hill buildings. So hill buildings or asymmetric buildings undergo a lot of torsional motion, but that is the torsional motion of the floor, torsional motion of the slab, but not the torsional motion of individual elements. So individual elements will still fail in flexure and shear. So you require flexural and shear hinges. Torsional hinge is not necessary.
Which thing we have covered?
Yeah, for perfectly symmetric building, time period in the two directions will be same. Why our code? Yes, this is something controversial. Our code assumes that if the two periods are close or same, then there will be swapping of energy and there may be resonance like situation between the two sides. But that doesn't appear to be probable. We are doing a study and we performed 3D nonlinear analysis using symmetric and asymmetric buildings with mass irregularity. We could not find that. So this does not appear to be probable. But the thinking of the code is that if the two periods are close, then there may be swapping of energy between the two modes and there may be a resonance-like situation. So to avoid that, code says that the two periods should be different. But no other code, I agree, no other code says that. And maybe in future, I don't know, if the code committee is convinced, this can be removed from our code also. Again, similar question for tall buildings, when we can say it is stiff or flexible. There is no definition because these are relative terms, but definitely there is a limit on interstory drift. So any building which is having interstory drift more than permissible is definitely a flexible building and is not allowed. So if a building is having interstory drift within the permissible limits, then we can say it is acceptable. So then there is a question regarding 43 years return period earthquake. So I have not seen any relationship for 43 years return period earthquake. The relationship is for 75, I mean what I gave. But you can use those earthquakes in any case are so small. So whether it is 43 or 75 years return period, it will not make much of a difference. Okay, then there is one question that when a beam plastifies, what happens there? So you are familiar with the concept of plastic hinges in steel structures. And plastic hinge is different than a physical hinge. Physical hinge cannot take any moment. Plastic hinge can take moment up to yield moment. Beyond that, it cannot do. So when we were doing our pushover analysis, actually we were doing incremental analysis. So when I have said that we will apply a release, that release will be for the next increment of load. So till the previous increment, till the moment was my, it was acting like intact member. But in the next increment, So that pushover analysis was incremental piecewise linear analysis. So in successive increments, it will be 0. So it is not, that means it is not 0. At that plastic hinge, it is resisting moment equal to my. Somebody wants to learn multi-mode pushover analysis. Actually, multi-mode pushover analysis is a concept given, but it is not very successful. So there what we do, it is similar to mode superposition method. Only thing is that here we do mode superposition on the displacement corresponding to performance point. So do pushover analysis in different modes. Take the load proportional to different modes. Do the pushover analysis, get the performance point, you will get the displacement corresponding to that, and do SRSS of those displacements. That's it. And then use that displacement, but it's not very popular because it doesn't add much accuracy. Yeah, how long should be the input ground motion? Okay, so I said there was a statement in one of my slides that the ground motion should be consistent with the seismotectonic setup. So how the duration of the ground motion decided? The duration of the ground motion is decided by the magnitude of the earthquake which is causing that ground motion, then the distance. As we go away from the source, the duration of the ground motion goes on increasing. Then to some extent, it is also depending on the local soil conditions. So that's why we try to select only those earthquakes which have the similar magnitude, similar distance as is in my case, and similar site conditions. So the ground motion, duration of the ground motion will be automatically considered there. And then there is a question that while going through the journals, they see the values of 0.63G, 1.2G, etc. So what does that mean? So it means the same thing as our JAD. So only thing is that what our JAD is, that is also EPGA, effective peak ground acceleration. But keep in mind, it is not MCE. We have to multiply it by 1.5. So the maximum EPGA our code is considering, the peak ground acceleration our code is considering, is 1.5 into 0.36. So 0.36 is the JAD value in zone 5. 1.5 is the factor. So it becomes 0.54. But now more studies are being done, and it has been observed that that is on lower side. In zone 5 of our country also, we expect something close to 1G. And the code is under revision. And you may see something like 1G or 1.1G or 0.8G and 0.9G in our code as well. What will happen to our existing buildings after that? That's another question. Okay, then there is a question regarding target response spectrum creation in ETAPS. Target response spectrum cannot be created in ETAPS. That is to be obtained either from the code or from site-specific seismic hazard analysis. So we can perform a deterministic or probabilistic seismic hazard assessment that will give us the target spectrum. If we are not doing that, then whatever spectrum is in the code, that is our target spectrum. So if you want to perform pushover analysis for, let us say, DV, then our target response spectrum will be the spectral shape. So what is given in our code as SA by G is actually not a spectrum, it is spectral shape. You multiply that by JAD and 1.5, then it will become response spectrum for MCE. And if you divide by 2, then you will get response spectrum corresponding to DVE. And that you can input to ETAPS or SAP as the target response spectrum. Question is what to do if modal mass participation is not we are not able to achieve more than 65%. You have to go for time history analysis. That's the only possibility. So if we do not get 75% mass participation, that means pushover analysis is not applicable. We have to do nonlinear time history analysis. How the compression steel contributes to flexural strain of the plastic hinge. So in compression, the ductility of steel is more than ductility of concrete. So it is governed by concrete. And then there is another issue. The steel, in case of earthquake, the moment is reversing. And due to reversal of moment, the same steel is in compression and then it is in tension. So it undergoes tension and compression, tension and compression. So there is low cycle fatigue. So that's why we limit the strain in steel in compression as well as in tension. So although the code says that we will not use any steel which is having total elongation less than 14.5%. But in nonlinear analysis, we use the strain in steel in tension maximum up to 5% and in compression maximum up to 2%. Because if we allow more than this, then it will fail in very few cycles. It will not be able to survive the full duration of earthquake. So the maximum strain we permit is 2% in compression and 5% in tension. Yes, then there is a question about load control and displacement control pushover analysis. Okay, so pushover analysis is essentially displacement control, but in some cases where we do not expect our structure to yield, for example, gravity load, there we can do a load control pushover, or where we expect that the load we have will not cross the peak. Okay, there we can do a force control or load control pushover also, but actually it is displacement control. Why pushover case is defined as nonlinear static? Interesting. This is called nonlinear static as well as single mode. So here what we are doing, we are performing equivalent static analysis. So we convert this into an equivalent single degree freedom system and try to calculate the behavior in such a way that the static response is matching with the dynamic response. So here we do not take into account the dynamic characteristics of the building. What are those dynamic characteristics? One is the hysteresis, because hysteresis is based on the cyclic nature of earthquake. So we do not take into account hysteresis. We do not take into account the inertia force. So that's why we call it static analysis. In 3D building, what is the correct point of application of load in pushover analysis? So the load should be applied in the same way as it will be acting during earthquake. So during earthquake, where the load will act? During the earthquake, the load will act at every mass point. It is inertia force. So wherever mass is there, it will act. If I have to apply a single load, where should I apply? I should apply it at the center of mass. So it should be proportional to the mode shape, and it should be applied at the center of mass when we are talking about 3D model. I think, okay, what is the difference between secant period and effective period? So secant period, how do we obtain? If I take a point on pushover curve and join that point by origin, it gives me the secant stiffness. And if I use that stiffness to obtain the period, it will be secant period. So secant period will be changing throughout the deformation. As the deformation increases, the secant period will go on changing. So what will be a single period which will represent the behavior of that structure, the displacement of the structure. That is our effective period. So effective period is single period. Secant period is a variable period. It varies. It depends upon the displacement. So if I sort of take an overall period which is representing the overall behavior of my structure, that I can call effective period. So that is effective period. In some methods, secant period corresponding to the peak displacement is taken as the effective period. But actually that's not correct. Peak, our effective period will be somewhere in between. It will be in between the initial period and the secant period corresponding to the peak displacement. Because that is the range in which the period is changing during earthquake. So problem with earthquake is that the period does not remain constant. The period changes. So if I have to use single period, I have to choose an appropriate period somewhere in between, and that is our effective period. Hinges in case of RCC inclined members. So a RCC inclined member is subjected to axial force, bending moment, and shear force. So we have to take the same hinges as we assign in case of column. So it is subjected to axial force as well as moment. So we have to take interactive PMM or PM2 M3 hinges. Or if we estimate, if we find that the bending moment is along one direction only, it is in one plane only, then we can have PM interaction hinges. Otherwise, in general, we should assign PM2 M3 or PMM interaction hinges. Again, there is a question that do we assign M3 hinges only in primary beams, or we assign M3 hinges in the secondary beams as well? So as I said earlier, that we should assign hinges at all probable locations where yielding can occur. So if you are sure that the secondary beam is not going to yield, you can avoid hinges. But otherwise, you assign the hinges there also. If it is not yielding, that hinge will not come into force. That hinge will not come into picture. There is no upper limit. It depends for using pushover analysis. It depends on the mass participation. So if the mass participation is more than 75%, you can use pushover analysis. There is a question, can we use pushover analysis for structures whose fundamental period is greater than 1 second? Yes, definitely. So we can use, and in fact, in that range, around 1 second, this method is most accurate. Well, I cannot answer why a company is not developing. That only company people can tell. Okay, this is interesting. What if my structure is governed by wind forces? Then how can I benefit it from nonlinear dynamic analysis? Suppose there is an irregular structure, but it is being governed by wind forces. Then is nonlinear analysis necessary or not? Is it required or not? So see, when you are saying that it is being governed by wind load, then you are comparing wind load with earthquake load. So which earthquake load you are taking? Are you taking reduced earthquake load or the elastic earthquake load? What value of response reduction factor you are taking? If the wind load is greater than the earthquake load with R is equal to 1, then you need not to consider ductile detailing or nonlinear analysis. But if the earthquake force you are taking with response reduction factor R, then it has to follow the code, or you have to perform a nonlinear analysis. Okay, because you are taking advantage of R and you have to ensure that that R should be available. So wind force is larger than the reduced earthquake force, not larger than the actual earthquake force. Then there was a similar question maybe later or here which we can use, that if we are using pushover analysis or nonlinear analysis or code exceeding buildings, is ductile detailing necessary or not? So let me tell you, for design of new buildings, the nonlinear analysis cannot be used to overrule or override any requirement of the code. So whatever requirements of the code are there for good buildings, that you have to follow. Okay, so far. So it is, as I said, that originally this method was used for evaluation of existing buildings. So existing buildings might not have followed the code. That's why all those possibilities are there. But the policy is that whatever are the good design and detailing practices, those have to be followed in new buildings, irrespective of whether you are performing nonlinear analysis or not. So then you may ask, then what is the advantage of nonlinear analysis if I cannot do that? The advantage of nonlinear analysis is that you will have more confidence in the design, and you can optimize your design. You can make your design safer, more safe than what you are obtaining from the code. That's what the advantage is. But you cannot avoid ductile detailing. You have to do ductile detailing, whatever analysis you are doing. If you are not getting a performance point using the demand and capacity curve, that means your structure is not able to resist that earthquake. So if you are not able to get performance point, that means the reduced demand curve is not intersecting with the capacity curve, then that means that building will fail in that earthquake. So you have to revise your design. Okay, how to deal with composite material buildings. So buildings with composite materials or new systems, you can perform nonlinear analysis because response reduction factor is not given in the code. But for nonlinear analysis, you will require backbone curve and hysteretic model. For that, you have to perform adequate amount of testing on that new material. So whatever composite material you want to use, you have to have access to the experimental results. Either those experiments are conducted by somebody else, you can use those results if those are available in research papers or in some reports. Otherwise, you have to do your own test. Then only you can perform nonlinear analysis and design of the building. Okay, there is an interesting question that in case of shear walls, walls are assigned fiber hinges, and we do not consider shear deformations there. So is it okay to consider fiber hinges and to ignore the shear deformations? So I think here some clarification is needed. There are two issues. One is the shear deformation and another is the shear failure. Shear deformation is much easier to incorporate because shear deformation means that you have to consider the shear stiffness or contribution of shear deformations in the stiffness matrix. So all our members, frame members, include shear deformations. And in that table where I have given you the stiffness modifiers for flexure and shear, there is a modifier given for shear area. So you can modify that. Shear deformation will be considered automatically. For that, you need not to provide hinge. So hinge is not to consider the shear deformation. Hinge is to consider the shear failure if my building is failing in shear. So if the shear wall is having less capacity in shear, then there is a possibility of shear failure. In that case, you have to assign a shear hinge also So in addition to the flexural hinge, you can assign a shear hinge. Okay. Or alternatively, you have to do capacity design for shear wall in such a way that the capacity in shear is larger than the capacity in flexure. And in that case, the shear wall is not yielding in shear, it is yielding in flexure. Some people, most probably, they are involved in research. They are interested in modeling of nonlinearity of joint. So in case of concrete RCC members, nonlinearity of joint can be modeled easily, as I said, that by applying appropriate length of rigid elements as far as the stiffness is concerned. But if the joint is failing in shear, then it is very difficult to model. There are several papers you can learn from that if you are interested. But in design of our buildings, we will not go for that. We will ensure that the joint does not fail in shear. The joint does not go into nonlinearity. And for that, we have to calculate the shear stress in joint, and we have to design the joint for that shear stress. So we will allow, even if we are using nonlinear analysis, we will not allow failure of all the components. So that hierarchy of strength, strong column, weak beam, no failure in shear, those will still be there. So nonlinear analysis doesn't mean that you can do anything. You need not to bother about any capacity design or anything. So please don't take that notion. Okay. So still you have to ensure that your member is stronger in shear than in flexure. Your joints are stronger than the member, so joints are not failing, and there is adequate confinement. The detailing is also proper, so those cannot be compromised. These are good design principles. These cannot be compromised, whatever method of design you are using. Okay, this is a relevant question. From where can I get time histories of earthquakes occurred in Indian subcontinent? So we have a website run by our department by the name PESMOS, PESMOS, PESMOS. So you search for PESMOS on Google, it will take you to that website. You have to register there, and then you can request the ground motions, they will send you. So they will provide you access to that website, and then you can search which ground motions you are interested in. Oh, how ANSYS has advantage over ETABS or SAP. Okay, so there are two types of structures, two types of systems. One we call skeletal structures, which are generally frame structures or truss structures. So some of the softwares which were written by civil engineers, those were focused on analysis of skeletal structures. So originally SAP was there, STAD, ETABS, Perform. These are the software which have been written for skeletal structures. But they have added some capabilities of continuum. What are continuum? Continuum are those systems which are having distribution of material in 2 or 3 dimensions. For example, a slab, a shear wall, or soil. These are continuum structures. So, and mechanical systems. So when people are modeling machines, they are generally modeling as continuum. Those cannot be modeled as frame elements. So they model those using solid elements. So there are software written by the people with mechanical engineering background, like Abacus, ANSYS, okay. And these are the software which primarily cater for continuum systems. So these softwares are good for nonlinear analysis of continuum. Whereas the ETABS and SAP, These are good for performing nonlinear analysis of skeletal structures. But there is a problem when we have to analyze a structure with foundation, with soil. So if I want to analyze a soil structure interaction problem, then none of the software is good enough. One caters to one aspect, another caters to another aspect. There is a software called Midas, which is very commonly used for design of bridges. That has this facility. It has a good library for continuum elements as well as skeletal elements. So both types of softwares have different area of application. Okay, but both can do nonlinear analysis of the respective type of structures. What is the maximum allowable displacement for shear wall under nonlinear regime? The limit is not on displacement. Limit is on rotation in the hinge. So you can see the rotation, and depending on the height, displacement you can calculate, because displacement is simply rotation into height. So that displacement will depend upon the height. So the limit is on inter-story drift ratio or the plastic rotation, plastic hinge rotation. So those limits, plastic hinge rotation limit is available in SC 41. I have shown you the table. So that is there. There is no limit on the total roof displacement of a building. There is nothing like that. So limits on displacement are in terms of rotation or ratio, inter-story drift ratio. Yeah, there is an interesting question. How I can do nonlinear analysis instead of a pipe straight section made with plate elements? I don't think you can do that. That you can't do even in SAP. No, SAP you can do because it has a layered nonlinear shell element. So, but STAD I don't think it has. The best software for this is Abacus or ANSYS, which is because it is a continuum system. When you consider pipe at the level of the wall of the pipe, then it is a continuum. So it should be treated as continuum. I don't think you can use acceleration loading in pushover analysis. So pushover analysis has to be done in displacement control mode. Okay, why the multi-mode analysis is not applicable in case of buildings where contribution of higher modes is there? The reason is that the multi-mode analysis is basically mode superposition method, and superposition is valid only for linear systems. In nonlinear systems, superposition is not valid, and pushover analysis is a nonlinear analysis. That's why theoretically this any type of superposition is not valid, and that's why the multi-mode analysis is not valid. What these people tried, those Chopra and others who gave this multi-mode analysis, they thought, okay, how much error will be there if I assume that mode superposition is valid in nonlinear analysis also. And they found successively, subsequently, by other researchers also, that error is large and the method is not reliable. That's why this multi-mode analysis is no more used. If your pushover analysis is not valid, you have to go for time history analysis. What is the significance of performance point? So performance point is telling you what deformation and hence what damage your structure will undergo under a given earthquake. So performance point is telling you the displacement or the damage or the performance of your structure during earthquake. So that's why it is so important. Well, if your torsional irregularity is more than what is permitted in the code, you have to perform a 3D nonlinear dynamic analysis and ensure that the performance is within acceptable limits.
Yogendra sir,
Yeah,
we have to give some time to Gadgil also.
yeah.
So maybe some of the questions which are balanced, they can be answered separately by
I
mail.
think
But
I
I
have
know the
already covered. Almost everything is what was relevant to my I have covered. So I'm done actually.
Such no.
Gadgil sir, ask again.
I
Sir.
Sir, any questions you want to answer specifically?
वाटतं आपण
Or
प्रश्नांना
केले.
उत्तर लेखी द्यावीत मला वाटतं.
Oh, we have all we have covered, I think. He's including his questions also.
Remaining we can send later on.
Yeah.
Yeah, it's very difficult to differentiate between our
there is
questions.
no.
We both talked on the same topic.
Same topic, correct. We can have a concluding remarks, sir, and we can. Hello, Jain sir.
First of all, Yogendra sir and Gadgil sir, thank you very much for very interesting lecture. Even the topic was same, the overall approach to the subject was totally different. In the sense, Yogendra had complete basic theoretical base, and Gadgil sir had demonstrated one example, or rather 3-4 example, and explain how we have to go further if you have to go to the end of the Pushover analysis. Now I thank all the participants, and even now I can see nearly 230 participants are still there, and so that shows their interest and concern about the subject. In fact, we were very much worried whether we should keep full day webinar or not. Secondly, whether we should have a regular 10 minutes or 15 minutes tea break or not. And we said that everybody is at home, so whether we can avoid that, but next time we can review this situation so that a longer session can be definitely held. So I thank all the participants. I request them to complete the feedback from.
Will be sent.
And send it back so that we can organize the next workshop or seminars in a different and better fashion. And we had been calling Yogendra Singh once in a year, but at that time there was a limitation of time and travel, and normally he had to spend 3 days whenever he used to come to Mumbai. So now we can probably invite him more frequently. So I'll talk to Yogendra Singh right now. He doesn't not seen on the screen. With this, in fact, I also had Dr. What we said that we had been calling you once in a year, but in the revised mode of communication, we can have you more than that. And with today's our experiment on webinar, we can think of a little more effective planning of webinar. In fact, I had 3 questions for you, which I'll mail to you instead of now extending patience of all the participants. So please accept our sincere thanks, and we'll meet again. Thanks from our entire team. And what you are seeing in the thank you side is the all director, unit heads, and volunteers who always work very hard for the workshop. Comparatively, the efforts for comparatively little lesser, but still good amount of efforts go in whenever we organize any webinar. So please send your feedback forms, and Yogendra Singh sir, we will talk tomorrow or day after, and or we can talk after the feedback comes and we can plan for the next one. Gadgil sir, thank you. तुमच्याकडे बरेच there are so many topics in his list, and we have to check what is the next interesting topic we have to take it. So thank you very much.
Thank you very much, sir. Thank you.
Thank you, sir, and thanks a lot for continuing this activity.
Yeah.
Even under this difficult situation. So we will continue this, and hopefully we will meet face to face also soon.
Sure.
Thank you so much.
Thank you.